Here.
Okay, I think we can get started. So welcome to the afternoon session. Our first speaker is Professor B. Parameshwar Nair from the City College, and he'll tell us about gauge theories in 3 dimensions and 4 dimensions. Please.
Thank you, Sujoy. I guess I follow that clock, right? That one? Okay. 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 So let me start by congratulating Bal again. More than 6 decades of very impressive work. And so I'm really privileged to have been his student and also to talk at this meeting. As I mentioned in the morning, there will be many talks covering very many diverse topics in physics. And for my talk today, I want to choose a topic that is fairly old, trying to understand the non-perturbative structure of gauge theories. But it is a topic, although it's old, seems to have some continuing interest. So I'm going to talk about gauge theories in 3 dimensions and in 4 dimensions. Basically, we are going to focus on the non-perturbative structures. We're going to introduce gauge invariant field variables, which makes the factoring out of gauge transformations fairly simple and straightforward. In 3 dimensions, which is 2 space and time, it will be done in a Hamiltonian framework. The advantage to doing that is because the spatial manifold can be treated as a complex manifold, and that will play a big role in what I'm going to say. In 4 dimensions, to use similar techniques, one needs to consider the functional integral, and I will focus on 4 manifold, which is CP2, the complex projective space, which is the simplest case one can analyze. Okay, since of course it's a short talk and I won't go over so many details, let me just alert you to what the results would be like. So the key results we find in 3 dimensions, we will have an analytic formula for string tension. This is something of an old result. I have worked on this topic, as some of you might know, on and off for many years. The formula for the string tension, I will just introduce it to you again, just to refresh your memory if you have heard me before. But what is relatively new is an analytic expression that I will show for the Casimir energy in the non-abelian case. Okay? And I will also compare all these things with the lattice results, so one can see how good the approach is. In 4 dimensions, the key result is the emergence of a 4-dimensional Weismann-Witten action, which controls the integration measure for the theory. The implications of this are still not very clear, but this is very, very new work, so it's still, some of it is still ongoing work. Let me start by giving credit where credit is due. The results on 2+1 go back a long way. Many collaborators, Dimitra, Karabale, Chanju Kim, Alexander Yelnikov, Abhishek Agarwal, and a few other people as well. The Casimir energy is relatively new work that's done with Dimitra. And the 4D work is very recent work with Dimitra and a very brilliant graduate student of mine, Antonina Moj, who I will let you know will be on the market next year, looking for a job. Okay, so let's talk about the two-dimensional case first. We are looking at spatial manifold, which I can take as R2 or the complex plane C. And it's well known that we can parameterize gauge fields in this fashion. Take the complex combination A1 plus IA2, and that is the holomorphic derivative of a matrix times its inverse. And this is the conjugate expression for that. Okay? The matrix M we are talking about, I'm going to look at the group SUN for most of what I do. This means that the matrix M that I'm talking about is in the complexification of the group of interest, which in this case is SLNC. So this is a well-known parameterization in two-dimensional physics. The main advantage of this parameterization is that if you look at how gauge transformations act, it is, of course, inhomogeneous in the transformation in terms of the vector potentials, but it is homogeneous by left multiplication of the matrix M by a unitary matrix G. Okay, so that simplifies the analysis of the gauge invariant degrees of freedom. Okay. So what this tells us is that if I take M dagger M, which I call the matrix H because it's Hermitian, you notice that the G cancels out in the middle. This is a gauge invariant quantity. It parameterizes the space SLNC mod SUN, and that's where your gauge invariant degrees of freedom lie. Okay? That parameterizes the space of gauge invariant fields in the problem. We are, of course, trying to do quantum physics, so we need several ingredients. One is that we need to know how to normalize the wave functions of the theory in the Hamiltonian picture. Then we need the Hamiltonian, and of course, once you set those things up, you would like to solve the Schrodinger equation. And so this is just, by and large, textbook kind of method. The technical difficulties is what we should, the technical difficulties are what we can overcome by using this parameterization. Okay, so what do we do? To understand the normalization of the wave functions, you look at the space of gauge potentials. You write down the metric on that. This is the standard Euclidean metric you would write down on the space of potentials. And that's the correct metric. It's given to you by the Yang-Mills action as the correct metric to be used for the space of gauge potentials. In terms of our parameterization, it looks like this. Notice that when I take a variation, I'm going to get some derivatives of delta M from here and the d bar of delta M dagger from here. Those derivatives become covariant derivatives. I can bring it to this form as shown here. Notice that the two extremities of this expression here, with the d bar d inside, in between, the two extremities form SLNC Cartan metric, basically. Okay? So if I use this result here, then I can factor out, well, I can write the volume element in a very simple way. Just from looking at this expression, you see that I'm going to get the determinant of this operator here, and from these two, which form the SLNC Cartan metric, I get the Haar measure on SLNC. Okay, so this is the form of the volume measure. The Haar measure on SLNC, you can factorize exactly. The unitary part can be factored out. There is a coset part, and the determinant in 2 dimensions can be calculated exactly as the Vezumino-Witten action, exponential of the Vezumino-Witten action, where C sub A is the adjoint Casimir for the group. Okay, so this is an exact expression that one can derive. It has been known for many, many years. It goes back to work by Gavetsky and Govenin. And I have shown here for completeness the expression for the Vezumino-Witten action. Okay, this is a standard, well-known thing. The 3 form is here. There is a 2 form, the metric-dependent kinetic term here. Okay. Notice, of course, that the CA, the adjoint Casimir, made of the structure constants, is actually 0 if you look at the abelian case. Okay. Everything else would go through, as I said before, but this is the point of departure between how the abelian theory and the non-abelian theory would work out in the end. Okay? That's a really important point. Okay, what do we do then? We can look at the Hamiltonian in the same way. We go back to using these variables that I showed here. And in terms of these variables, you can construct the Hamiltonian. It's a simple matter of chain rule, so I'm not going to go through all the technicalities. The E square term, which you remember, it's delta by delta A square kind of thing when you do canonical commutation rules. So that becomes this term, which I have displayed in terms of first derivative with respect to a current and a second derivative. The current is what is the current that would appear for your Weismann-Witten theory. So that is the variable of interest, and in terms of that, you can write that. And the B square term is this term here. So everything can be transformed to this new variable J, and you can construct the Hamiltonian in terms of that. The quantity M is E square Ca over 2 pi, and this is the basic mass scale in the theory. Okay? So far, everything has been done exactly. There's nothing that, sorry? There is no Chern-Simons. This is just Yang-Mills theory. I have added Chern-Simons terms in some of the papers, but we'll talk about that later. Okay. The point is, based on this, we can now do a systematic expansion scheme. And I should also emphasize everything is done with regularizations, everything, there's nothing worrisome here in terms of potential divergences or anything of that sort. Okay, so very good. So what do? We take an ansatz for a wave function, e to the p, I write it in this fashion. P involves quadratic terms in currents, cubic terms, and higher orders like that. Some arbitrary, a sum of all arbitrary powers of the current J. You put that into the Schrödinger equation, and you can solve, which seems a little surprising, but it is actually doable. And if you do, the quadratic term has a kernel, which is given here in terms of that mass scale I introduced. The cubic term is also displayed here. I can do systematically higher terms as well. Okay? So the point is that one can actually write down the vacuum wave functional of this theory, at least within certain approximations. This expression is what should be used for the long wavelength modes or low energy modes of the theory. So this is the regime of the theory which is not accessible by standard Faddeev-Popov perturbation theory. Okay.
You are not putting without infrared effects at all. Now there are, instead of the vacuum, this is the vacuum
with no super selection sectors. I mean, it's trivial super selection sector.
Yes, but so this is not really the long wave integral. The long wave will necessarily involve super.
Not in this case because there is a mass gap. There is a mass which will cut it
But
off.
you don't know that will happen with infrared effects.
This mass is already here in the Hamiltonian.
That doesn't matter. I mean, what I mean is there could be fluctuations at infinity, which will not be showing up in this. So I have to, this is a vacuum. You're writing the vacuum in.
I'm writing the vacuum wave function.
But I can twist it with a large gauge.
Oh, sure.
And that will create effects at
I'm not looking at twisted sectors.
Yeah.
That really goes back to the question that TRG asked.
Yes.
If you want to do twisted sectors with Chern-Simons terms or
You
things
don't
like
need
that.
Chern-Simons. You can just take the vacuum and twist
That's
it with a
right.
large
If you
gauge
twist it, then of course things will change. But what I'm trying to do is, let's just do the simplest case. Okay. Pure vacuum, zero charge sector, nothing, no super selection sectors, and see what happens, right? That has been, for 50 years, the big problem. If we can solve this, at least we make some progress. That was the idea. Okay, so what happens with this wave function that we obtained? Well, we can calculate the expectation value of the Wilson loop, which is displayed here in terms of the current J. This is the Wilson line. I calculate the expectation value, and you get an area law immediately. And not only that, you can read off the string tension, this coefficient sigma here. That's the area of the curve. And it's given by this simple expression in terms of the Casimirs. R is the representation of the Wilson line. Ca is the adjoint Casimir. Cr is the Casimir for representation R. And E is the coupling constant. Okay? So you get this simple formula. And you can ask, does this make any sense at all? And the answer is it does seem to, because people have done, using supercomputers, extensive simulations of this string tension in 2+1 dimensions. Most of it is due to Michael Tepper at Oxford, but there are many other authors. Here too, I think Haridas and Manjumdar did the work here actually, high precision calculation for AC2. And in all these cases, in every single case that has been done, which is 22 different choices of groups and representations, the answer that is within 2% of this formula. Okay? Yes? This is dominated by the quadratic term.
So this is the quadratic approximation.
That's correct. Yeah. Okay. We have calculated in one of our papers the corrections. I won't discuss it today, but we can talk privately about it. Corrections are extremely small. This formula is not changed significantly. Okay. So that, yes, please.
Product of two Casimirs actually.
Because the adjoint Casimir is always there because the interactions is a pure gauge theory. So the commutator term brings in the structure constants of the algebra which give you the adjoint Casimir. And it also appeared in the mass parameter here that I showed you. Okay. And the R, the representation R appears, of course, because I'm choosing a Wilson line in representation R.
Sure.
Yeah. So they both play a role in the final answer.
Okay, thank
Okay. Okay, so more recently we did this calculation on Casimir effect. So the idea is you do the same thing you do for Casimir effect in electromagnetic theory, parallel plates. Of course, we are in 2+1, so if you like parallel lines, you put boundary conditions appropriate to conducting plates, which is this boundary condition here in terms of the field strength. The electric field, tangential electric field is 0, and you can calculate the Casimir effect. Okay? So here is a formula for the Casimir effect as a function of the distance x, which is in terms of string tension expressed here. The LIs are polylogarithms, and so this is an expression we can analytically calculate. Notice the exponential here. There is nothing, no parameter that we can adjust here. There is no adjustable parameter at all. The coefficient A is, if you like, difficult to calculate exactly. In the lowest order, it's equal to 1. So we can take this expression, compare with the lattice calculation. Okay, that was what motivated us to do the calculation in the first place, because there was a possibility of doing a lattice calculation, which is very numerically very expensive, so people don't do that very often. But what we find then is that the two lines are practically on top of each other, as you can see from here. The red line is the lattice simulation done by Chernobyl, Goy, Molotov, and Ian. And the solid blue line is our calculation from this formula. And in particular, the existence of the mass gap is crucial. The exponential here. If you make an error there, it's exponential. The two graphs will diverge dramatically. Okay? So the fact that they agree so well over a whole range of distances tells you that these exponentials are really pretty much exactly what they should be. Okay? So that is really one of the nice things. So again, the agreement, if you try to quantify it, it's to within 1%, actually. The parameter A, just one sec. The parameter A, I said, is equal to 1 in the lowest order. Here I did a best fit, that's 0.97. So even if I simply take the lowest order result, it's going to be just within 3%. Okay? So with no adjustable parameters, we can get this to agree. Yes, please.
I wanted to ask about the mass gap. So it just came out in 3D naturally?
Yes, because the coupling constant has a dimension already. So there is no problem there. Okay? Okay. Okay. So that's about 3 dimensions. I want to see if we can do this in 2+1 or 3 dimensions, can we try to jump to 4 and see what we can say? Okay. Of course, it's going to be a much more difficult problem. But one of the things I want to say is that instead of looking at the complex plane, let's look at CP1, the complex projective space, which is the sphere, SU2 mod U1. And if you do that, then the parameterization for the gauge fields can be written again in terms of a matrix M, but with translation operators R plus R minus, which are right translations on the group. Okay? You can parameterize the CP1 manifold by an SU2 group element, use that as a coordinate for the space, and then in terms of translations on G, I can write this parameterization. So this is the question we want to ask, because this follows straight away from the complex structure and the group structure of CP1. Can we do that in 4D? Okay. So that can be done, but why choose CP2? Well, I want to say that CP2 is a reasonable space for various reasons. It is a complex structure, which is very crucial for what we do. It's a group coset, SU3 mod U2. So many things we can do just using group theory, which is always a nice thing to do. The Fubini-Study metric on CP2, I have displayed here with a parameter R, which is the radius, which if you take large, it tends to flat space. And even further, CP2, of course, has reduced isometries compared to flat space, but CP2 modular conjugation is actually the 4-sphere S4. Therefore, it's not too far from what we might want to do in a more isotropic situation. Okay. So because of these reasons, we thought, okay, let's try CP2. Okay. So what do we want to do? We want to use. So there is if you take CP2 and mod out by conjugation symmetry, but complex conjugation of the coordinates, involution, yes, then that gives you S4. So that's a theorem due to actually Arnold, I believe. Yeah. Okay. So some old theorem in math. Yeah. So at some point, maybe it would be useful to use to get to S4 in this fashion. So what do? We take SU3 to coordinate as the space, which means I have a 3x3 matrix.
S4.
Yes.
From this theory,
how
do I go to?
You have to ensure that all the results are invariant under a conjugation of the coordinates.
Okay.
All those results will descend to S4. Okay, that's the idea. And so hopefully that can be done. Okay, we haven't carried it out here, but
Okay.
that is my hope.
But the topology is far different, right?
Yeah, of course.
So there could be
But the
other effects, particularly non-perturbative effects.
That is correct. There are things you can do on CP2 which are not invariant under conjugation,
Right.
which won't descend to S4. But hopefully some of what I'm saying will actually.
Okay.
Okay, so we do right translations on the group element G, split it into the usual way, the SU2 isospin part, T8 hypercharged part. These are like the local isotropic group rotating frames on CP2. And the T4 plus IT5 and T6 plus IT7 and their conjugates, they will be the translation operators. So those are the complex translations along the complex coordinates of CP2. Okay. Now, if I were to look at functions on CP2, they have a mode expansion I can do in terms of the Wigner matrices, the standard group representations of the group elements in arbitrary representations. Some of them, that's a standard Peter-Weyl theorem. The state on the right, W, must be so chosen so that for functions, W must ensure invariance under U2, SU2 and U1. Okay, because they have to be functions descend to the base space CP2, so one has to do that.
Can I ask a small?
Sure.
Yeah. So the choice of complex structure is something new, extra that we don't see in usual perturbation theory, right? Because this.
That's right. Yeah, and that's going to.
S4 perspective, we don't need it.
That is correct. But
So
you will see that it's very crucial for me.
But there's no unique complex structure. So if you vary, the results won't change.
Oh, you mean vary the complex structure?
Yeah.
You could vary the complex structure, but for CP2, that's hard to do, right? Okay. But I could take a large R limit and then start varying the complex structure. Yeah, that I can do. Yeah. Okay, so what I was going to say was, for functions, it's therefore straightforward. We take these matrices, we take the right, the action of the T matrices. The U2 part on the right should be 0, so that gives you functions. And then you can expand functions in terms of various things like this, standard representation theory. Okay, What about vectors? Vectors, remember, U2 here is the local isotropy group rotating the frames. Therefore, vectors must transform non-trivially under U2. Okay. How do they transform? They must transform exactly as the translation operators Ri and Ri bar did, because those will tell me what the vectors are like. Okay. So that means I should have something that is a doublet of SU2. So it has the two components for the vector and their complex conjugate. So that gives me the 4 components I need. And then the hypercharge should be plus or minus 1, because that's what these translation operators R and R bar had. Okay? So in terms of that, therefore, I can construct vectors in the following way. Some of the vectors I talk about will be simply derivatives of scalar functions. So that's okay. That's Ri and Ri bar acting on some function f. But there are others. For example, if I think of SU3 representations in this usual way we do with some indices up and some indices down, then in that language, P plus 3 P type, P plus 3 ups, P down, or the other way, they will also contain states which have this property, doublets of SU2 with y equals plus or minus 1. Okay? So you can expand in terms of those two. So a general parameterization of a vector then takes this form, where here on the right side, I have a P plus 3P representation, and here I have P plus 3 type. Okay? I here takes values 1, 2, indicating that I have a doublet of SU2. Okay? And it has the correct hypercharge. So in terms of this, you can write this. And if you actually work out what these states are, these are not derivatives of functions or anything, but they are actually the conjugate derivatives. So if I have the I-type index, it's the R bar acting on some quantity here, which is again not a scalar. But nevertheless, you can see that it's more like the divergence of a tensor. So if you do that, you can bring it to this form. Okay? So gradient of a function, this is like the curl, if you like, of a tensor or a divergence of a tensor. So you have this parameterization here, and then the conjugate is this. Okay? So you can actually write down a general parameterization which by construction we know captures every degree of freedom. You're not losing anything at all by doing this. Okay? So these are rank 2 antisymmetric tensors. So this is basically like the Hodge decomposition on the CP2 space. The important thing is that there are no harmonic terms or anything. Okay? You can generalize to the non-abelian case by simply noting that this is what you want in the abelian case, which will be like the small, it's like a small perturbation of SLNC around the identity. So you can integrate on SLNC and write down the full parameterization like so. So this, I claim, is a general parameterization which mimics what we did in 2 dimensions in the 4-dimensional CP2 case. Okay? So that is the idea that we want to use. I won't go too much more into details of this. I have written this in a slightly different way. The gradient terms are shown explicitly, and here the divergence of the tensor I replace by A and AI bar, which are these quantities here. Okay? The reason I wrote it like this is if A and A bar are 0, then you can easily see F02, F20 are 0. So anti-self-dual instantons are also described by this parameterization. So it's not restricted to perturbative fields alone. Okay? There are non-trivial configurations you can construct. Okay. So what are the gauge invariant degrees of freedom? We get these 3 guys here. One is our old H M dagger M. And then from this little a and little a bar, you get phi, which I put some extra matrices to make it gauge invariant. And these are the degrees of freedom. Okay? So we have factored out the gauge transformations in a completely straightforward way. And now we can ask, can I calculate the integration measure and write down what happens in this case? Okay? Here the integration measure is a functional integration measure for the full functional integral, not the wave functions. Okay? Again, you start with the Euclidean measure, standard measure. You write in terms of these variables. You can bring it to this form. Again, there is a factor involving variation of M dagger. And if you look at this structure, there is a matrix made out of these operators here. I'm not going to go too much into details. And then these are the variations of the fields, this psi diagram psi. So you can compare this metric with this one without the m, and you can see that the two will differ in volume measure by the determinant of this matrix here. Okay? So we can write down, therefore, the integration measure that we need in 4 dimensions in this fashion, and you can factor out, as we did before, the gauge transformations and get the invariant measure written in this fashion. So far, everything is, again, exact. The question is to calculate the determinant of that matrix. Okay? That, of course, is the tough part, and it's not so easy to do. In 2 dimensions, one could do it exactly. Here, I'm going to do it with some sort of perturbation theory to see what we can get. And what emerges, well, it's not difficult to do, but, well, it's a lot of work, but it can be done. Okay? So the simplest strategy is to write this determinant formally in terms of a function integral over some action. This is not the Yang-Mills action. This is an action we use just to rewrite this determinant in this fashion. There are 2 types of fields which enter. One is C bar and C, which are scalars, having 0 hypercharge. And then there is B and B bar, which have hypercharge 2 and -2. Okay, those are the antisymmetric rank 2 tensors, which for CP2 have only 1 component. Okay. So if I take this action and just start calculating the determinant, I should get the integration measure. Yeah. So what do we do? Well, that's what we do. Not easy to do because you need exactly the propagator for d bar d. Remember, there is, oops, where did I go? Yeah, there is d bar d here, so I need the propagators for these things, and then there are a bunch of vertices. So we write down the exact propagator for CP2 for both cases, for scalars as well as the tensor fields. This can be done. It's nice group theory calculation. In terms of homogeneous coordinates, I have displayed them here. These capital Z and capital Y are homogeneous coordinates for CP2. For y equal to 0 and y equals -2, I have shown here. You can do an ultraviolet regularization by a point splitting method. And we add a Wilson line to get it gauge covariant as well as, so the point splitting is done to ensure that you still have Levi-Civita covariance on CP2. Okay? The Wilson line is added to ensure that you have gauge covariance on the space. So at the end of the day, you have a regularization scheme that respects all the isometries of CP2 and gauge invariance. Then you simply sit down and calculate. Okay? And here is what you find. There are several terms that we can find. So there is a finite term, which I will talk about. There's a divergent, linear divergent, log divergent, and then a bunch of additional finite terms. The first finite term here is what I'll focus on. The others are fairly easy to dispose of. Actually, maybe I should talk a little bit about gamma 1. Let me talk about gamma 1. So there is a divergent term here, which is quadratic divergence, which is a mass term for your gauge field on CP2. Okay, a gauge covariant mass term is possible on CP2 because it has reduced isometries, and that is what we find here. Of course, it comes with a divergent coefficient, so you had to renormalize the measure to make it finite. Why do you need to renormalize the measure? That is standard. That is exactly like renormalizing the Faddeev-Popov part of the Lagrangian that you do in perturbation theory. Okay, and in this instance, the mass that you enter here, the finite mass after renormalization, is the dimensional transmutation of the theory that you see in the language of the integration measure here. Okay? So this is the non-perturbative way to see the dimensional transmutation. So that is this parameter here. I'm sorry? That's right. Here I don't have a scheme dependence actually. Okay. Okay, so lambda QCD, if what people call lambda QCD should be expressed as a function of this parameter m, okay? And that's something we are actually calculating now, and we should be able to do it fairly soon. But what is more surprising, and this is what I want to focus on, just one more minute, is that there is a finite dimension 2 term. Okay, so there is a dimension 2 term which is the leading term in terms of dimension counting, but it enters with a finite coefficient, and that is actually a four-dimensional Bezumer-Witten term, okay, which is quite interesting and a bit of a surprise, okay. And we can calculate the coefficients. It is finite. I have displayed the numbers here if you like. I tried to do it with also an infrared cutoff if you like. Then the point is that what this tells you is that if you look at modes with momenta less than the mass that I put in with that mass term I showed, which means less than what passes for lambda QCD in this framework, then the theory is dominated by the Bezumer-Witten theory. Okay? So there is a kinematic regime of the theory where essentially the Yang-Mills theory is dominated by this Bezumer-Witten theory, four-dimensional, with a finite mass term, a finite coefficient. And then this is just a Haar measure on SLNC mod SUN. Okay? So that is the key result that we find. The implications are not very clear, but the 4D Bezumer-Witten theory has a long and interesting history. It goes back to the work of Simon Donaldson. My student Schiff and I looked at it many, many years ago as well. There's more recent work by Costello on implications of 4D Bezumer-Witten theory. The critical points of this theory are anti-cerebral instantons. So there is something going on here in a regime dominated by this, but we are not quite there to give you a crisp, nice answer like the 2+1 case, not yet anyway. So I'm going to stop here, and I won't go through the points again. Thank you, and happy birthday, Bob.
Thank you very much, Parameswaran. We have 5 minutes or so for questions or comments.
Do you find confinement?
In the 4D case?
Ah.
Okay. It's hard to say. I'll tell you why. Okay. If you try to calculate the Wilson line, the 4D Bezumer-Witten theory, there is no exact calculation of the Wilson line I can do. However, if I trace the calculation step by step and compare with the two-dimensional case, you realize that the same reason why the 2D theory gave confinement exists in the 4 dimensions. And that you would get, presumably, confinement. But I cannot give you a formula for string tension.
Will it last if you take from CP2 to S4?
I believe it will, actually, because the Wilson line expectation value is not sensitive to the complex structure at the end of the day. Okay?
Okay, we have 2 questions, Bal first and then Denjo after that.
CP2 and the sections of CP2 are compact. Okay. In the compact space, there are no charges. So one cannot even define what is meant by color in this situation.
Yeah. So confinement.
Excuse me, let me finish.
Yeah.
People say that Wilson line and so on test color, but I have no idea whether that has anything to do with QCD. It is seems to be some private activity, which has nothing to do with the algebra observables you started from.
Well, thousands of people do it. It's not very private.
Let me say, okay, because there is if you take R3, there are colored states you can find.
Sure.
And I think what has to show is that the Hamiltonian of the theory diverges on the colored states to show that there is confinement. I have seen no such proof anywhere in the literature. Okay? And in fact, this Wilson line business, I don't know why it is QCD. If it is QCD, show me what are the algebra observables in that theory, and I don't know. Okay? One has to show the connection to a Hamiltonian, to a time evolution operator. That is not shown. Okay? So, anyway, this is my opinion. It may be that quantum field theory is not correct.
Well,
I have no problem with that.
No, there are several definitions of confinement that one can use.
But let me finish.
Yeah.
So CP2 and S4, CP2 and S4 has no color. Color is zero, like electric charge being
There's
zero.
no color charge. But
so
you can,
there is no question of color.
No, but you
color
can,
confinement. There is no color. How do you see it? There is no operator for color. It is zero. So you can't see it. In quantum theory, you need an operator to see such an object. What is that operator? I don't know anything like that because of compactness.
Yeah, I mean, strictly speaking, you're not defining color.
We have to be strict on this,
No, because there are different ways to think about color confinement. When people talk about confinement in QCD, you can ask, what is it is at the end of the day a matching between an unconfined regime that you describe using perturbation theory to a confined regime where there are no colored states. So it is that transition that we want to understand, right? That's how it is practically implemented in terms of how QCD is applied, to describe hadrons.
Yeah, if
So-
it can be done. I mean, color is seen in jet. Jet physics.
No,
seems
color
to-
is not seen in jets if I use your strict definition.
No, but
Co-
at least there are indications of color.
Exactly.
Well, I think
But
that's
here there is no such indication because there is no operator to test it.
no. The Wilson line is the operator that you
That
use.
doesn't test it. That is something. I don't
Okay,
know
Bal,
what
we
it
can
is.
postpone this later. I think Denjo had a question. Sorry.
Just before I ask my question, just a comment on the Wilson line. The Wilson line is telling you the force between two separating quarks, separating two passive quarks to probe quarks. So there is some indication of. Sorry? Infinitely massive, if you wish. Yeah, well, there are two probe quarks, however you want to.
Right.
So if it grows, yeah. I'm wondering about CP2. CP2 naturally has a curvature, and I'm expecting there will be a trace anomaly in your computations in the end. It showed up in your dimensional transportation. Conformal invariance of the classical theory was broken. But
Right.
is your Wessomino-Witten term related to that conformal
Yes,
trace
yes, yes.
anomaly?
It's related to the curvature in the sense that what you are doing here is to upgrade your 2D Wessomino-Witten theory to 4D by wedging everything with the Kähler-2 form. And the Kähler-2 form, as you recall, is actually one of the curvature components, the hypercharged component of the curvature. So that does play a role in the construction of the Wessomino-Witten action. Okay, so that curvature is important. If I take the large R limit, I will still get a Kähler structure, so I'm not getting flat space with full isometries of flat space. It will be reduced isometry still. And the idea was to take larger limit and use the conjugation symmetry to see if I could relate it to the isotropic case. That's the line of thinking that we hope we can go. Okay. But as I told you,
Yeah, very nice talk. I
this is very new result, so we have many more things to say.
One last question.
So in 2+1 dimension, I remember Singer had an analysis for the mass gap, right? And
Yeah.
there it was a differential geometric analysis, and he ran into some infinity problems
Correct.
for the sectional curvature.
Correct.
So does that kind of infinity
No,
show up in your
no.
analysis?
And I'll tell you exactly what happens with Singer's argument. Singer's argument is also closely related to the Feynman argument that Feynman tried to do. So Feynman thought that the configuration space could have some kind of compactness, and the E square term is the Laplace operator, and therefore it would develop a gap because I'm defining it in a compact space. Singer told him that doesn't work because there are spikes running off to infinity. You can have long wavelength excitations which exist on these spikes. Okay? So Feynman basically gave up at that point. What we find is that, granted, there are spikes. I constructed the spikes explicitly to show they exist and what they look like. But the computation of the measure shows they have zero measure. So just as it happens with the x square, y square type potential, as you go along the spike, the transverse curvature keeps on increasing, and therefore the 0-point oscillation in the transverse direction lifts it, and therefore it has no effect at all. So Singer's argument is mathematically correct, but at the end of the day, irrelevant for the physics.
Sorry, Alok has one final question.
So maybe I missed it, but small a was the anti-self-dual gauge field part, and capital A was the self-dual gauge field part. You had a slide earlier in the.
No. I'm not using self-dual things.
Yeah, but there was a split, I thought. That
Yeah,
you-
this
yeah,
one.
Yeah.
I'm just pointing out that if you set little a to 0, you get basically anti-self-dual instantons.
I see. So,
Okay.
yeah, I see.
But so long as little a is not 0, there's a lot of...
Yeah. But could we look at subdual Young-Mills in this language and then do a anti-subdual perturbation on it using this formulation?
The problem is then I had to change the complex structure. I had to do a conjugation on the
Right.
CP2. And that I haven't tried, but it may be possible.
I see.
Instantons do exist on CP2 as well as anti-instantons. So there must be a way to do that, but I just haven't had time to think about it very
Because
much.
there's a twistorial way too, right?
Yeah, that's right. Yeah.
Sorry, there's one online question, I think. If someone can read it out. Please go ahead. Please.
Sorry, I guess there's...
Yes, please go ahead.
Can you hear my question? Can you hear me?
Yeah.
Yes.
Okay, good. Hi. Great talking to you, thanks very much. But I have a question about the projection onto S4. When you're doing the Wilson lines on CP2, are you using spin C structure? Because CP2 doesn't admit spinners.
Oh, that's indeed correct. But I'm only looking at, I'm not looking at spinners. I'm looking at probe charges, as Denjo was saying. So the Wilson line I can define in any representation.
Okay, so you're not using
Yeah,
spinners.
but if I do, I mean, we haven't gotten to the point of looking at quarks. If we do, you're absolutely right. We had to use a spin C structure, which I believe can be done without too much trouble. Okay?
It can be done in CP2, but I mean, I've heard before that you can get S4 by projecting down from CP2, but I've never thought about how, I mean, somehow you must get ordinary spinners on S4. presumably by projecting a
Right.
structure.
Oh, that's a
I've never
point
thought
you're
about
talking
how that
about.
works.
How does the conjugation symmetry work with the spinners?
Yeah.
No, I haven't thought very much about spinners, I have to confess. No.
Okay, we finished 5 minutes early, but we are 5 minutes over time now. Sorry about that.
Okay, S2 cross S2, yes, I did think about that to some extent. And it's, again, a puzzling space because S2 cross S2 modulo permutation symmetry is CP2. So you might say that, well, that could also be done. Okay? But the problem for me was factoring out the gauge transformations is much harder there. Okay? Whereas this one is much simpler. So we tried S2 cross S2, but this is easier.
Okay, let's thank Parmeshwar for a great talk.
Thank you.
So our next speaker is Giuseppe Mamo. It's going to be an online talk. So let's hope it goes through well. Is he online? Vasan, help. He's muted at the moment. Could we unmute him, please? And could you share his slides? We cannot hear you yet. Please give us a second. Vasan, can you share his slides? He says that he may have trouble. Yes. Can you unmute him? He's unmuted. Oh God. No, he's unmuted, but we cannot hear him. We cannot hear you, Giuseppe. could you try sharing your slides as well?
Slide we can open here.
Okay.
But what's gated?
What about the slides? Can you just try?
Yeah, yeah.
Sorry, give us just a second. Well, in the meantime, Brian Dolan has his hands up in case he has a question or a comment about the previous talk. He's unmuted. No, he's unmuted. Oh. See. So it's just us that we cannot hear him. We can't hear him. Sorry. Ask him what.
Yeah, the file of not open. Yeah, the file downloads.
Non lo so, non mi sono. Peppe, sono Alessandro, posso darti una mano? In qualche modo?
Guarda, non lo so che sta succedendo, perché io ho fatto tutte le cose che si potevano fare, quindi...
Okay, now we can hear you, I think.
Perché loro ti sentono su Zoom?
We can hear you, Giuseppe. I hope it is Giuseppe.
Can you hear me now?
Yes, yes. Okay, so
So, can you also see the screen or not?
yes, we can. So our next speaker is Professor Mamo, and he'll tell us about mathematical structure of Schwinger's quantum mechanics.
Well, now that we have solved at least this communication problem, you know that I could not be there in person because the embassy here refused to issue the visa for me because I did not have the clearance of the Minister of Exterior Affairs. Anyhow, I am happy to be here and to celebrate along with you Bal's birthday. I must say that I first met Bal something more than half a century ago. It was 1970. At that time, I was writing my laureate thesis, but my advisor went to Dubna, so he was not around. When he came back, he said that he could not deal with what I had prepared, which was something on extension of Lie groups. And so Bal saved me by suggesting that I could write a cohomological approach to projective unitary representation of the Galilei group and the Poincaré group. And actually, because for the representation, for the extension, you have to use the automorphic group of the Galilei group. That was my first paper, which I co-authored with George Whiston, who was visiting, was postdoc here. Since then, with Bal, we have collaborated on over more than 60 papers. We have written 3 books together. And obviously, in all these years, as you can see, more than 50 years, it's clear that it's like a family. So we are the Italian branch of the family of Bal. Now, let me say something about the collaboration. The work I am talking on has been carried on with Florio Ciaglia, Fabio Di Cosmo, Alberto Ivor, Luca Schiavone, and Alessandro Zambini. Now, because we only have a limited amount of time, let me say what is the main message of what I'm going to talk.
Professor Mamu,
which
could I
is a-
please interrupt you? Could you please share your screen yourself? That would be.
Yes,
No,
can you see here?
no, the file cannot be seen at the moment.
Oh,
If you could share your screen.
No, screen is shared, sir.
I mean,
The PDF is not visible. Can you minimize this? Can you minimize this Zoom thing? Minimize, sir. Minimize.
we are seeing a different window, not.
now yes, but what about this? Can you see now it?
No, what we can see is just the Zoom on the browser.
Now?
Hello, sir.
Yes?
Can you press Command Tab? It will switch the.
I have reduced.
Okay, otherwise we will share from here. So others you should need to. That's also fine. It's. Oh, there is no way to switch. We have the file, sir. But
So then, if you could stop sharing your screen, we'll try to share the screen from our end, if it's possible.
Okay.
Sorry about this. Okay, now I think we can see the screen.
Please go to the previous slide. The previous slide, please.
Okay, just a minute.
No, yeah, thank you. Now, Schwinger started, let me give a brief history of his approach to quantum mechanics. He was teaching quantum mechanics in Harvard in the 1950s, and he gave a course at Lesuche Summer School in 1955, and notes appeared in a book format in 1971, and they were reissued in 1991. He had also been lecturing at UCLA in the 90s when he moved from Harvard to Los Angeles. And the notes were given to Bert Angler, who edited the book, and the book appeared posthumously in 2000. This edition has a very informative prologue of 25 pages, where the philosophical attitude of Schwinger appears entirely. It is based on the transcript of a public lecture that Schwinger delivered in the early 60s. Now, in the previous reissued version, what Schwinger did, he said, the only thing I have done is to change the notation from MA prime A to A prime A, as you see here. Can you see by mouse or not? Well, and then eventually he gave this format. Can you hear me?
Yes, Pepe, we can hear
thank you. Okay. So what he did he changed the notation of a measurement symbol, and in the 60s, he published few notes on the proceedings of National Academy of Science. He decided to publish in National Academy of Science because being a member of the Academy, his papers would not be sent out to referees and would be published directly. Now, next slide, please. Next slide, please. Here. So the idea of Schwinger was that all the conceptual setting of quantum mechanics from the algebraic point of view can be completely understood with the Stern-Gerlach type of experiment. And actually, what you read here is exactly what he wrote. That is, Stern-Gerlach type of experiment accomplishes a self-contained physical and mathematical development of the general structure of quantum kinematics. And you are, all of you are familiar with this simple example, what is being given here, which is silver atoms which are being collimated, and then they are sent through a magnet, and you have the usual up and down part of the spin, so spin up and spin down. Next slide, please. Now you see, if you perform successive Stern-Gerlach measurements, what happens is that you can actually select up atoms and lower atoms. And so you have, you construct in this way an up selector and a down selector. Next slide, please. If you now use a homogeneous magnetic field, then you can essentially, via precession, you can flip. And so you go from whatever schematized here, from an up atom to a down atom. So you have now two selectors and two flippers. Next slide, please. So you see that if we represent up atoms and down atoms by unitary vectors, the four SG Stern-Gerlach measurements may be described by the action of these four matrices. You see that the first two are selectors, while the last two matrices are the flipping. So if you now look at the composition of these matrices, they close on what is called a groupoid. So in this respect, a groupoid comes out directly as a representation of the spin Stern-Gerlach experiment for spin 1/2, which I have shown to you. Now, usually, a schematic representation of a A2 groupoid, let's say, is the arrows which you can see here. And so the arrows connecting one to the others are what I have called the flippers, and the other two are the selectors. Next slide, please. So now you see here that, no, the previous one, please. Okay. Now, this is another instance of groupoid. This is a Grothian-10 scheme in spectroscopy. In particular, this one is for lithium atom. Now, let me say that the mathematical structure was not identified by Schwinger as a groupoid, but he immediately says that you can deal with the linear composition of measurement symbols, and therefore, obviously, he goes immediately to the groupoid algebra rather than to stick with the groupoid, which we have seen associated with Stern-Gerlach measurements. Now, the transition from the groupoid to the groupoid algebra erases the specificity of the groupoid. And this is true, obviously, because different groupoids may give rise to the same groupoid algebra. By the way, also at the spectroscopic level, what Heisenberg did was, again, to represent the groupoid. However, because Born and Jordan knew matrix algebra, they decided to translate into a product, the so-called matrix algebra representation of quantum mechanics. And obviously the groupoid, again, disappeared from the picture. So in both cases, what happened was that even though the experiment would give the structure, would give you immediately the structure of a groupoid, the way people at that time considered the groupoid was via the groupoid algebra. So the groupoid was essentially removed from the picture. However, one thing remained in both pictures. This was actually what Born was stressing, that the main relevance or the main difference between classical and quantum mechanics was that quantum mechanics was actually dealing with the transition quantities. So now, from our point of view, it's clear transition quantities are two-point functions. And obviously, what happens is that the elements of a groupoid are indeed related to 2 point. So next slide, please. Before I go on to move to more formal aspect, I would like to make a remark that one of the most important contributions to mathematics of the last century was to notice that it is possible to study mathematical structure per se without realization or representation or identification of symbols with physical property. This remark, trivial as it may appear, should be always present when mathematical structures are being used in theoretical physics. Mathematical modeling is extremely valuable to ensure the coherence of what is being elaborated, especially in dealing with quantum phenomena where the intuition is not very useful because phenomena are often very counterintuitive. Now, next slide, please. My favorite example to illustrate previous remarks is provided by the Heisenberg-Weil algebra. You see, at the mathematical level, the Heisenberg-Weil algebra is simply a three-dimensional vector space with the commutation relation that you can see here. From this vector space, you may construct the dual space, the tensors, the antisymmetric tensor, and the antisymmetric forms, and on V star, a dual basis would be given by forms which are characterized by the formula that you see here. This is Cartan description of a Lie algebra. Now, at this abstract level, you can develop an exterior differential calculus at a pure algebraic level, and an application of this algebraic differential calculus was used in the PhD thesis of Gianni Lanti applying to gauge theory and relativity. Next, please. Now you see what happens with different realization of the Heisenberg-Weil algebra. If you realize it with Poisson bracket, you get classical Hamiltonian mechanics. If you realize with d by dx, x and 1, you get differential operators, therefore partial differential equation and wave equations. If you realize as a per point 3, you get wave mechanics. If you realize in terms of matrices, you get matrix mechanics, but you can realize in terms of creation and annihilation operators, so you go to quantum field theory. If you take the dual point of view, you get a contact structure which may be used to describe dissipation and thermodynamics. So the point is that all the abstract construction that I performed earlier, they can be carried over to the realization that we have given. However, if you work with the realization, what happens is that there are additional properties which are spurious, which do not belong to the initial problem. So this is to say, please, the next slide. This is another instructive example that I would like to give, where the identification with the physical variables give rise to different physical systems. This was actually considered this book with Balachandran, Alstern, Bosturas, Kagerstam. You can see if you write the Poisson bracket, which I have written there, if you identify position and momentum in one way, then you describe the electron monopole system. But if you make a different identification, you describe a massless spinning particle. So again, this is to say that the mathematics is extremely useful. However, to talk about physical system, you need to perform the identification of physical variables. Having said this, let's go back now to groupoids. When you go to groupoids, obviously, the literature now is quite vast. However, there is a nice book which has been written by two physicists, Alberto Ibort and Miguel Ángel Rodriguez. And here, actually, there is a chapter where you can find most of what I am going to say here from the point of view of mathematics. Now, what is a groupoid? Well, a groupoid in categorical terms would simply be a small category where each morphism is invertible. Now, I don't know how much this definition would appeal to a theoretical physicist, but in any case, you can think of a groupoid as two sets, one which is the set G and the other is set omega. Now, going to our previous pictures, it's clear the set G is the set of transitions. The set omega is the set of the initial and the final states, for instance, in the spectroscopy diagram, or the state vectors, we would say. And so what happens is that for each transition, you can define two maps, one which associate to the transition the initial point, and the other which associate to the transition the final point. These are called the source and target. And essentially, when composition, you have seen in the spectroscopic diagram that not all transition can be composed. But when the composition is possible, what happens is that you get an associative structure. So roughly speaking, a group point is a generalized group, and the identity is replaced by unit morphism at each point. And so you have a situation where the groupoid, being a set of transition, contains also transition which do not correspond to going from one state to another, but remain with the same state. And so in this sense, this will be the new unit, and you have as many units as the element of the space omega. Next slide, please. Now you can see that you can use these two target and the source maps, and you can define morphism which will end, or if you think of them as arrows which will originate from X, or arrows which will terminate in X. And so, roughly speaking, starting from here, you can mimic all the properties and all the definition that you can give for a group. In particular, by requiring differentiability properties for the G and omega and the maps, you get Lie groupoids. If you require continuity and topological properties, then you get topological groupoid. If you put measure on the two spaces, you get measurable groupoid, and so on. You can simply, by making appropriate requirement, you can generalize the groupoid to the category of other spaces. Next, please. So for Lie groups, you have Lie algebras. For Lie groupoids, you have Lie algebroids. And if you consider the case of a pair groupoid, that is when you simply have two copies of the same manifold, this is a Lie groupoid, and the Lie algebroid is the tangent bundle. Now, if you consider the dual bundle, obviously you get the phase space, and it's clear then that classical physics can be formulated on Lie algebroids, and you recover whatever you can do at the classical level directly on at the level of Lie algebroid, and therefore of Lie groupoid. Next, please. Now let me go back to the picture of Schwinger so that we can try to go. We had some problems. So it is interesting in a sense that Schwinger, as I stressed already, decided to present everything with what he called simplified physical systems, and introduces compatible quantities. And the definition is that they do not destroy the knowledge that you get by prior measurement of the other. A complete set is a set where if there is any other properties which is compatible, then it must be a function of A1, A2, AK. And this state is simply the maximum knowledge that you can get by a complete selective measurement. So you see, this assumption are enough to characterize essentially what in operator language we would say a maximal set of commuting operators. And the idea of identifying state is via preparation method, what in my Stern-Gerlach experiment was the collimators. And then obviously you have the selection. The selective measurement will produce states which were up or down. So in a sense, whatever Schwinger does is clear he has in mind the Stern-Gerlach type of experiment. Next, please. Now, by using the expression in terms of bra and cat, the symbols, the measurement symbols of Schwinger have the form which I have written here, that is with a bra and a cat. Now, it's clear that the composition can be defined either on the left or on the right. Usually, Schwinger used to prefer the left action. And if you take the full set of this transition and you organize in a matrix form, next please, you see you get a matrix which is associated with a groupoid. Each element, each entry is a rank 1 operator in our language. So the arrows now may be thought of connecting AK with AJ. And similarly, so now you see, you can from here visualize immediately what is the inverse of the target map and the inverse of the source map. They will be rows or columns, and there is clearly an immersion, a canonical immersion of the object, let's say, into the morphism. Now, here one should make a comment, because it's clear this is an effect of what I said earlier, that having used the notation in terms of bra and cat, it seems natural that a measurement symbol gives you bra vectors and vector and cat vectors. However, as Schwinger himself writes, he says a jump step forward has been made by viewing each measurement as a product of two symbols of a new type, one which is a bra and the other which is a cat. However, it's clear that they are distinct type of vectors because one symbolizes a creation act while the other one symbolizes a destruction act. Now, it's clear that what he has done is simply played with the notation and has been able to go to the Hilbert space on which this object may be represented, essentially without paying very much attention. Now we know that there would be a possibility to make this rigorous either by using GNS construction or by using what is called the fundamental representation of the groupoid. In any case, you see here the danger of introducing a given notation or a given additional structure through the representation. That is clear that at the level of groupoid, there are no vectors. You have to define them properly, in one way or the other. Next, please. Now, what I will do next is to give you another, please, next slide, please. May I have a next? Okay. You see, this is another notion. This is very much as we constructed the tensor spaces on the Lie algebra, the Heisenberg-Weil algebra, which I gave. You can construct what are called the two groupoids. And essentially, you take now all the elements of previous one, and you make them to be the element of the objects. And so now you construct transition from one object to the other. Now, you can see immediately that this is needed when you consider generalized states for quantum systems. Indeed, the transition from one to the other here, they are called channels. And next slide, please.
Professor, you have 5 minutes.
Next slide, please. So, if you select a different complete set of compatible physical quantities, then you get a different groupoid, which may be represented Bj, Bk, the way I have written here. And so you have a new morphisms. And it is possible clearly to go from an A representation to a B representation by means of unitary transformation. Now, putting together the groupoids associated with different complete set of compatible physical quantity is necessary to write the evolution. And this essentially gives you a new groupoid. You see, the previous groupoid essentially rely on a maximal set of commuting observables. So this means that inside what we could call the groupoid algebra, you select from the beginning a maximal abelian subalgebra. And a groupoid in this respect contains not only all the observables, but also a choice of a maximal abelian subalgebra, which is what you need to make the measurement. Next, please.
Professor, you have 3 to 5 minutes left.
Well, yeah, I mean, we lost some time, but I can interrupt at any time. Now, you see, if you want to describe a physical system, you have to introduce state observables and the probability function. Next, please. Next slide. Okay. So, in the case of the Stern-Gerlach experiment, it's clear you have these abstract groupoid written in terms of vectors. And now by selecting maximal abelian subalgebra, you can go to different representation. Next, please. You see, this would be concrete realization of the different groupoid. And now you see that they are associated with sigma 3, sigma 1, sigma 2, and the other with what we could call a combination with a normalized vector, so that you can act transitively on all these different choices by using the rotation group. Next, please. Now, to implement the dynamics, you need to introduce what is called an action groupoid, which is a quite general notion. And essentially, you define a groupoid by using a group which acts on a set plus 2 copies of the set. You can see how you can see the definition here. And now that you have an action groupoid, it's clear the dynamics can be written on the action groupoid. Now, I will simply, just to show how general and how useful is the notion of groupoid, show you how the groupoid emerges naturally if you go from probabilities to probability amplitudes. Next, please. You see, usually we have on any measured space, if you take the wave function, you construct a probability measure. In discrete cases, you have the square root of the probability in terms of an amplitude and a phase. But if you now consider a quantum formulation of classical probability vectors, you would associate with every probability vectors the operator that you see here. Now, to consider the square root, obviously we have to take the square root of each element, which is what we call identified with the classical, because they are associated with a maximal set of commuting operators. Next, please. Now you see, I have written in a matrix form so that by taking the square root of each one of the elements of this diagonal matrix, you get the matrix downstairs. And so the square root of the diagonal matrix in terms of operators, let's say, gives you exactly the groupoid. So again, the groupoid in a natural way represents the square root of the quantum representation of a classical probability operator, probability vector. Next, please. You see there are other ways to consider the square root, to go from probabilities to probability amplitude. And in this way, you consider the unitary group, and this was used by Asorey, Faki, and myself to deal with topological order and mixed states and open system. Next, please. So now, having put groupoids in matrix form, of course, you can, as I said, generate the groupoid algebra, but you can also generate a star algebra in terms of convolution product. The two algebras are isomorphic, and obviously, having recovered a star algebra from the groupoid, it's clear that the groupoid formulation is fully equivalent to the usual one in terms of C-star algebras or in terms of Hilbert spaces. I did not have time to, I had not planned to actually deal with evolution, even though the action principle elaborated by Schwinger is quite an important contribution of Schwinger, but you have to wait for that. Now, the extension to continuous spectra or to field theories, you will have to wait for the talk by Fabio Di Cosmo and Alberto Ibor, which is what is written in next slide. And I conclude here. Happy birthday, Bal, and I hope to see you very soon.
Thank you very much.
That's it.
Are there any questions for Professor Marmo? We are running late, but we can take a few questions. Okay, if there are no immediate questions, let's thank Professor Marmo again. So we'll break for tea right now, and we'll be back in 15 minutes.
Okay.
Thank you. Thank you very much.
Bye-bye.
sharing anything for next talk?
We do not know. We might end up having that.
Skin, right? Is the one, right? Okay. Where it's yeah, making it. ஏதோ ஒன்று கூடிய ஹலோ ஹலோ சார் அவர் எங்கேயோ போயிட்டார் போலையே Yeah, too. அவர் ஷேர் பண்ணல அவர் மியூட்ல இருக்காரு அங்க வருது இல்லையா
அவரை கோஹோஸ்டா மாத்திடுங்க சார் அவரை கோஹோஸ்டா ரிமூவ் பண்ணிட்டு ஹலோ சார் கோஹோஸ்டா போட்டாதான் வந்து ஷேர் ஸ்க்ரீன் பண்ணுவோம்
அப்படியா
ஆமா ஸ்க்ரீன் ஷேர் பண்ண முடியும்
யாரு இவரு தானே
2 பேர் கொடுக்க முடியாது அவரை ஃபர்ஸ்ட் எடுத்து விட்டுருங்க ரிமூவ் கோஹோஸ்ட் கொடுத்துருங்க முன்னாடி ஸ்பீக்கர் இருந்தார்ல நீங்க இதை க்ளோஸ் பண்ணுங்களேன் சாட்டை க்ளோஸ் பண்ணுங்க மறுபடியும் முதல்ல இருந்தா பண்ண மாட்டேன் பார்ட்டிசிபென்ட்ஸ் போங்க இவரை வந்து கோஹோஸ்ட் வந்து எடுத்துருங்க இவர் தானே நம்ம எங்கே ஃபர்ஸ்ட் போட்டுருக்காரு அவர் போயிட்டு ஓகே இவர் தானே இப்போ ஸ்பீக்கரு இவரை மேக்கிங் கோஹோஸ்ட் ரைட் கிளிக் பண்ணி அப்படியே கோஹோஸ்ட்டை போட்டுருங்க மெசேஜ் போட்டிருக்காரு
அவர் கோஹோஸ்ட்டாக இல்லைன்னு போட்டிருக்காரு
Hello.
Hello.
Can you please share the screen?
Yeah, let me see. I'm trying to do that.
Yeah. Can you change the slide?
Yeah, okay, I will. Just a second.
Yeah. Yes, thank you.
So it works, right?
Yeah, it works. Thanks.
Okay, excellent.
இதுல தான் ரெக்கார்ட் போடணும் ஆக்சுவலா
Hello, Professor Kurcholu.
Yes, I'm here.
Can you stop sharing? Okay. Maybe we should try these. No, sir. We should check with the second speaker, right, Manuel? Sorry, because we hardly get any time between two talks.
Should be okay.
Huh?
Oh, okay, sure, you can do that.
Yeah, we have now 5 minutes. Yeah.
No, we have 3 minutes.
Huh?
Call the people inside.
Just hold on.
Okay.
Professor Asure, could you try putting up your slides and share the screen with us? Your mic is mute. Asure is.
He has to unmute.
Huh?
Next speaker you can ask.
I am asking, but he is not responding. Maybe he is not there.
Maybe the next speaker is after that.
Then speaker after that
Wait, I have it here.
is Badi Sedri. I mean, as of now, he is not there.
He's not there. Just go with the first speaker.
Yeah, we will keep trying. Okay.
Keep this one. This is good.
No, we need to have it for you, for all of you to hear.
That's
So then how will
you need a mic.
So it will definitely come feedback.
No, there should be another one.
Hello.
Hello.
Can you please share your slides?
Yes.
Welcome everyone. In the last session of the day, the first talk is by Sechkin Kurcholu. He will talk about chaos in mass deform ABJM model.
Okay,
Yeah,
so
please proceed.
I would like to thank the organizers for arranging and organizing a very nice meeting, and I also like to thank them for the invitation. So I would like to talk a recent work I did with my students And this is the outline of my talk. I will start with some motivations and background for this problem, and then I will introduce the mass-deformed ABJM model and give you some preliminaries. And I will show you how to dimensionally reduce this model from 2+1 to 0+1 dimensions. Then I will examine the chaotic dynamics of this model, and I will finish with some conclusions and outlook. So what are the motivations and background? So recently there has been quite a bit of interest in exploring chaotic dynamics emerging from matrix gauge theories. Well, some of these work was in fact motivated by an earlier result of Sekino and Susskind on fast scrambling of information by black holes. And more recently, it was in fact motivated by a result by Maldacena, Schenker, and Stanford, which essentially states that in the quantum setting, the quantum chaos is bounded in such a way that the largest Lyapunov exponent is bounded by temperature in the form that I have just written here, by 2 pi t. And in fact, it conjectures furthermore that systems which are holographically dual to black holes are maximally chaotic. That is, namely, they saturate this bound. So this was demonstrated for the Sachdevia-Kiteo model. And that's the only example that is known to date, which explicitly saturates this bound. But it's conjectured to be, or expected to be so for other matrix models as well, like BFSS matrix model. So, but it turns out that it is not easy to show, or not easy to access the quantum chaotic dynamics of these models. People have looked into classical chaotic dynamics in hopes of understanding the structure or the chaotic dynamics within these models further. So in one such paper by Gurari et al. From 2015, the classical dynamics was explored, and which this gives you an approximation to the quantum theory in the high temperature limit. And it was found that the largest Lyapunov exponent scales like the temperature to the power 1/4 here, with the numerics coming as the coefficient in front. Well, this essentially means that the MSS bound is violated only at temperatures less than a critical temperature around 0.015, while it remains parametrically smaller than the bound for temperatures larger than this. So there are some other works as well. There were some works on how to probe the chaos in BMN model, or how to, so we have also estimated some critical temperatures in some massive deformations of the BFSS model earlier. So today I would like to talk about a recent work examining chaos in the ABJM model, or the mass-deformed ABJM model. This model is a supersymmetric Chern-Simons theory coupled to matter fields, and it describes the dynamics of n-coincident M2 grains. Whereas its massive deformations has fuzzy sphere vacuum configurations, which are given in terms of GRVV matrices. And it also has holographic duals. So, well, let me give you some further information about this model. I will focus on the bosonic part of this model, and this bosonic part involves two SUN gauge fields, AMU and AMU head, and which are coupled to some complex scalar fields, Q alpha and R alpha. R runs from 1 to 2. They are bifundamentally coupled, and there's an SUN times SUN gauge symmetry. So here I have written down the dimensionally reduced form of this bosonic part of the action, which is dimensionally reduced starting from the 2+1 dimensions to 0+1 by considering that the fields are spatially uniform. And here you can see in the action there are the the Chern-Simons terms in the 0 plus 1 dimension. Other terms are, so D0 R alpha and D0 Q alpha are the covariant derivatives of these fields. And here V is a potential, which I will show you in the next slide. So the potential is essentially sixth order in these fields, and it can be compactly written in the form that I have just described here. Here, mu is the mass parameter of these fields, and there's a notation that's usually used here in this setting, which I have written for the Qs, and this is also the same likewise for the fields R alpha. So, and furthermore, I'd like to note that this action is already written in the 't Hooft limit, where the 't Hooft coupling in the 0 plus 1 dimensions, it is defined as n over V2, where V is the volume that we have integrated over in going from 2 plus 1 dimensions to 0 plus 1 dimensions. And but we have also scaled the 't Hooft coupling to unity, and if it needs to be inserted back into the action, we can scale the fields and the parameters in the theory so that we can introduce it back. So furthermore, this action is manifestly gauge invariant under SUN times SUN symmetry. Here you can note that these K are the Chern-Simons levels. They are quantized in of course, in the 2 plus 1 theory, but once you go to the 0 plus 1 theory, the effective Chern-Simons coupling is actually K times V2 over 4 pi. It's no longer quantized, and you can see that, in fact, these terms are gauge invariant. So let's go further. So this theory, if you look at the potential is positive definite, and there are two types of solutions which minimize the potential. These are given here. Either one can take R to be non-vanishing and proportional to the GRVB matrices, which I will introduce below, or one can take Q to be non-vanishing and proportional to the GRVB matrices. So these matrices are n by n matrices, and C is a constant which is given in terms of the K and mu here, as you can see, and the explicit form of these matrices are provided here. So these matrices fulfill a relation which I can note there, and just to give you a glimpse of how these matrices in fact form a fuzzy sphere, one can construct another matrix, say Ji, in terms of the bilinears of these GRVB matrices, and these Ji satisfy the SU2 algebra. So there is some further of course, details which I haven't included here. So let's go on. So one can, we are going to make the gauge choice in which the gauge fields A0 and A0 head are set equal to 0. This means that we have the Gauss law constraints, which are noted here, and the Hamiltonian in this gauge takes the following form, where PQ alpha and PR alpha are the conjugate momenta associated to these fields Q alpha and R alpha. So there is one important feature of these models, which we can immediately note at the moment, and if we try to scale the fields Q alpha, R alpha, and the fields X, which are coming from the dimensional reduction of the gauge potential from 2 plus 1 to 0 plus 1, and also the time parameter with the parameter rho, we find that in the massless limit, the energy scales as the minus third power of this parameter. So, since the Lyapunov exponent has units of inverse time, this suggests that one would expect in the massless limit the Lyapunov exponent for which describes the chaotic structure will scale as the 1/3 power of energy. So, and we will try to argue that this sort of a scaling will, in fact, essentially be preserved after we take into account the massive deformations. So I'd like to show an ansatz configuration which will facilitate the rest of the discussion. So in order to proceed further, we'd like to consider the following ansatz configuration, where the fields X and X head are essentially taken to be some diagonal matrices, which are multiplied by some real functions of time, alpha and beta. This part of the ansatz will be not important for us, but because we are going to see that the only equations which will satisfy the equations of motion will be such that alpha t and beta t will be equal to 0. So we can essentially set these fields equal to 0 in what follows. But for the rest of the fields, I take the fields Q and R to be proportional to the GRVV matrices in the way that is just written here, where there are two arbitrary real functions of time, QT and RT. So if we insert this ansatz configuration in the Hamiltonian, in this expression, in this Hamiltonian, and trace over the GRVV matrices, we obtain a reduced model, which is given here, where Vn is the potential, and PQ, Q and R are these functions of time, and PQ and PR are the associated conjugate momenta. So one can immediately observe some properties of this potential. First of all, it is symmetric under the exchange of the coordinates or the functions Qt and RT. Whereas if you change k to minus k, we see that there are terms which are proportional to 1/k changing their sign, but this can be compensated by switching Q and R, which means that the dynamics is going to be independent of the sign of K. So, and furthermore, we see that also in this reduced Hamiltonian, there is the scaling symmetry in the massless limit. So the Hamiltonian or the energy scale like the -3rd power of a scaling parameter. So let's look at so I have written down the Hamilton's equations of motion here for this reduced set of, or family of Hamiltonians at a given matrix level N. So one can, in order to get a feeling of the dynamics or how this Hamiltonian, family of Hamiltonians behave, one can explore the unstable fixed points in the phase space. So we have a 4-dimensional phase space here, and one can just solve for the fixed points first and see if there are unstable fixed points or not. And it turns out that there are unstable fixed points, which are given in this form, where the order of, I think, coordinates is such that these are PR or QR and PQ PR. So, and corresponding energies for these unstable fixed points are written here. In what follows, I will in fact focus on a mass parameter of equal to 1, but we are going to see how things will change according to the parameter K and also with respect to the matrix level N. So one further thing to notice here is that from the general theory of classical chaotic dynamics, one can expect that these the chaotic dynamics in such a system will try to appear at or above these energies of the unstable fixed points. So this is therefore an early indication on how or at what energies that we may be able to expect chaotic dynamics to develop from this Hamiltonian system. So this is just some further information. So of course, the Lyapunov exponents is a measure of the exponential growth in perturbations. So it's a nice way to understand the chaotic dynamics in Hamiltonian systems and as well as in other systems too. So here, as I have just mentioned, the phase space for these family of Hamiltonians at different matrix levels are 4-dimensional. And due to the Hamiltonian dynamics, there will be, so for this 4-dimensional phase space, there will be only one positively Lyapunov exponent. 2 of them will be 0, another will be negative. This is due to the symplectic structure or the boson structure. So, and so we are going to solve in order to understand the Lyapunov or to compute the Lyapunov exponents in these models. We do numerical analysis. So we solve the Hamilton's equations that I have just displayed here with randomly selected initial conditions. So we essentially pick around 100 random initial conditions at a given energy value and at a given matrix level. And we then calculate the mean of the time series for each and every Lyapunov exponent from all of these runs with different initial conditions. And in the simulations, we take a time step of 0.25 and run the code from time 0 to 3000. So I will, in the next slide, I will display the profile of the largest Lyapunov exponent as a function of energy over the square of the matrix levels. And I will focus on, say, n equals to 15 and 25 for the levels k equals to plus minus 1 and plus minus 2. So these are the profiles for k equals to plus minus 1 and n equals to 15 on the left and n equals to 25 on the right. So, so we have a fitting curve, which is given in the following equation. So as you can see, we have an offset to the exponential, not the exponential, but the power law, e to the power 1/3. So this offset is motivated. It can be motivated in 2 ways. One of them is to consider the fixed point energies, which I have just mentioned, and they are given here. So this is gamma n could be approximated by the fixed point energies divided by n squared, or it can also be motivated by using the virial theorem on the potential. So it turns out that these 2 numbers are quite close by. So, but we have, I think in the fitting curves, we have used the second one. So you can see that these fitting curves are quite good for the data points that we have collected. So this is then the, well, the behavior of the largest Lyapunov exponent as a function of energy over n squared. And here in the second slide, you can see that this is also good for k equals to plus minus 2, but at n equals to 25, there could be some data points which may be slightly off from the fitting curve. So, and here I have included some tables, which I will come back in a second. Let me go first to the next slide. Now, I'd like to go back to our initial motivations, and I'd like to tell you about how we can model the temperature dependence of these Lyapunov exponents. So if we go back to the matrix ansatz configurations, which I have written here, well, for the fields Q and R, well, it turns out that one can count the number of degrees of freedom in such a ansatz matrix configuration, and while keep also taking into account the constraints on the system, that's the Gauss law constraint, and as well as the R symmetry, which I haven't mentioned before, but R symmetry of the ABJM model, one can compute that then the number of independent degrees of freedom for this configuration goes like 7n squared minus 8, but since we are going to only need the large n behavior, that will be around 7n squared. So, and while since we are treating the system classically here, we can use the virial and equipartitions theorems together to write down the following inequality for the E over n square offsetted by these gamma n's are going to be less than 7 times the temperature. So by using this inequality together with what is expected from the MSS bound, we can put an upper bound on the critical temperatures. So by solving this equation, you see that this upper bound on the critical temperature is estimated by the coefficients of the fitting curves that we have determined. So the coefficients of the fitting curves are found from numerical analysis. And from those, we can estimate these upper bounds on the critical temperature, which means that for temperatures larger than the critical temperature, the MSS bound is safely satisfied, while for temperatures less than the critical temperature, they will eventually be not obeyed, right? So either at TC or a temperature less than TC, the MSS bound will be violated. This is rather expected. That's because we are treating the system at the classical level. So one can comment on the following fact, though. If we increase the matrix levels, which is essentially corresponding to taking the T Hooft limit in a better sense, we see that the critical temperatures decrease. So here in this table, you see, for example, for I have for n from 5, 10, 15, 20, and n equals to 25. So if you go look at the last row for in this table, the critical temperatures decrease with increasing n, and that's also the case for the k equals to plus minus 2. And furthermore, we see that if we increase the value of k, we also see a decrease in the critical temperature, or the upper bound on the critical temperature. So, well, so this is essentially, well, there is, of course, this is not the only ansatz one can work with. We have, in fact, in our work, we have studied another ansatz with similar results. But I just wanted to focus on one example for this talk. So to summarize, we have gathered some numerical evidence on how the largest Lyapunov exponent behaves as a function of energy, and we have estimated upper bounds on the temperature dependence of the Lyapunov exponents. So for the outlook, of course, it will be worthwhile to try to go beyond the classical dynamics and consider quantum effects. So there are some recent studies in that direction. So in these references by Pavel Buividovich et al. From 2018 and 19, there are some real-time techniques which are developed to go beyond the classical approximation. So the essential idea in these papers are to use a Gaussian density matrix to characterize the wave packet centers and the characterized by these wave packet centers and the dispersions. And by exploiting Wick's theorem, they are able to get a truncated set of equations of motion for the expectation values of these canonical variables and the dispersions. So this gives a non-perturbative way of accessing the quantum effects. And it turns out that for the BFSS model, they have found that the quantum effects that are computed in this manner for the BFSS model results in a decrease in the values of all the Lyapunov exponents. And they also predict that the largest Lyapunov exponent and all others vanish at a finite temperature, meaning that all the Lyapunov exponents remain below the MSS bound at all temperatures. So it will be interesting to try to extend these results to not only perhaps to the ABJM model, but also some other matrix models. And with my students, we have some preliminary approaches to some models involving fuzzy sphere times time. So it's like we start with some Hamiltonians with a scalar field on the fuzzy sphere where the matrices depend on time. So we like to understand if we can or how we can explore the quantum chaotic dynamics in such a rather simplified setting using the Gaussian state approximation. So this is the end of my talk, and I'd like to wish Bal a very happy birthday by the final verses of this poem Plea by Nazım Hikmet. And these are some pictures from Bal's and Indra's visit to Turkey from 2013. I think the one on the left was to the city of Antalya, and the one on the right is in the landscape is the Bosphorus Straits. Okay, thank you very much for your attention.
Thank you, Professor Kurzulu. Now we have time for questions.
Yeah, very nice talk. This MSS bound on chaos, etc., has very nice holographic interpretation. Now, given that the ABJM model also has a holographic interpretation, is there a way to understand this chaotic bound from the on the holographic side?
Well, so the motivation of at least the earlier work has been to understand the bound from the matrix model side always. So, but so that is why we have also focused on to understand the how the bound is satisfied or violated or not obeyed just by performing the classical approximation. But I don't know whether if there are some more recent work on to see how the bound can be understood from the gravity dual side.
Okay, thank you.
Any more questions?
I have a question from remote. I raised my hand.
Yeah, Bedele has it.
Can you? There is one. I probably missed something. A positive Lyapunov exponent doesn't mean chaotic behavior. Exponential map has a positive Lyapunov exponent. It does if your motion is on a compact bounded set, because then things cannot fly away. But I didn't see in the dynamical system with the PR and QR, the one that you wrote, that the motion is in a compact So did you try, for example, to make some simulation and to actually see that the motion is erratic or something?
Well, Fadil, I think you have asked me this question before
Yes.
in another talk or so. So
Yes.
as far as I know,
At this time, I was more, I looked more at the equation that you, at the system that you did, and I didn't see that it's compact. So,
so as far as I know, well, for Hamiltonian systems, just to explore the chaotic dynamics, a positive Lyapunov exponent indicates chaotic dynamics.
okay, because you are in a Hamiltonian, so you are on a torus.
Right.
Okay. So probably you
so-
gave me the same answer. Okay. Age
Yeah.
is running up, not only for Bal, but also for his students.
No,
Okay, thanks.
If there are more questions. From online participant. If there are no more questions, let's thank Professor Kurchulu again.
Thank you very much.
Next speaker is Manuel Asore. He will talk about energy preserving boundary conditions for field theories. It's an online talk.
Can you hear me?
Professor Asore, could you please share your slides, please? You have to unmute and speak.
Can you hear me?
Yeah, we can hear you.
I can share my screen because I have no rights to share. Can you?
Professor Kurchulu, you have to stop sharing your screen.
I have stopped sharing.
You have
No,
to
but-
make the speaker host, otherwise he cannot share the screen.
Yes, you have to
Manolo
make
seems
it.
to be the co-host now.
Yeah, we
It's
are
not-
trying to fix it, please.
Okay, now it works. Can you see now my screen?
Yeah, we are. Could you please make it full screen?
Yeah, I'm doing. Is it now full screen in your?
Yeah, now it's fine.
Okay.
Please proceed.
Thank you. So I'm very happy to participate in this meeting to celebrate the 85th birthday of Bal. And I met him long ago, and we started to collaborate in some subjects with common interest, and still we are still collaborating in some ongoing work. So we wrote 8 papers, and as I said, there is one which is going to appear soon. So one of the subjects we have common interest was the boundary effects and edge effects in field theory. And I'm going to talk about the same subject, although not on the papers we have written in the past. So the interest in boundary effect is not only an interest in particular models, but it's a general interest in physics and life, because all of us are made of organs. Each organ has boundaries, so we have not unlimited matter. All the matter we know is limited by boundaries. So boundary effects are important in all these branches of science. But particularly in physics, even looking at physics from the global perspective, we have in cosmology and astrophysics, we have now confirmation of the existence of black holes. And black holes involve surface effects. Also, we have horizons in cosmology, which again are physical boundaries in space-time. So we are forced to work in space-time with is a limited amount of space-time. So this is new because in the quantum field theory is essentially formulated in Minkowski space-time without boundaries. So we have to develop new tools and new ideas to deal with these systems which are constrained by the systems of boundaries. In recent times, there have been also interest in applications to condensed matter because, as you see in the screen, the plasmons and the plasmonic in metals and dielectrics is very current fashion in condensed matter. Also, the existence of energy currents in quantum Hall effect, where BAL has been working for a long time, is also something which is of current interest. Of course, topological insulators and the appearance of Fermi arcs in biosemiconductors is closely connected. The physics of this is closely connected to the gravitational anomalies, which again involves quantum field theory. So, but coming from fundamental physics, we also have boundary effects, which are more directly connected with the foundations of quantum field theory. Boundaries have a consequence, physical consequence, in the dynamics, quantum dynamics of these fields, and with several effects which are associated to this boundary physics, like Casimir effect, the black hole physics already mentioned, Hawking radiation, topology change, which BAL has been working a lot on this. So it's again something which involves topology to some extent is connected with boundary effects. And finally, holography, which has already been mentioned in this conference, especially in the context of the correspondence idea CFT. But what I'm going to talk today is something more basic, is something related to the foundations of the boundary conditions in quantum field theory. This is based on a recent work made in collaboration with my student, Fernando Esquerro. And the idea is that behind the boundary conditions for the evolution of quantum field theories, there are some principles essentially related to symmetries. You know, the Nether theorem is the first place where in the derivation you involve fluctuations of the field which oscillate also on the boundary of the fixed initial and final conditions. So it's just in the derivation of the Nether theorem where these boundaries conditions are violated. So the main principle used so far to fix boundary conditions in quantum field theory is unitarity. Of course, this is symmetry, time evolution of the quantum system has to be unitary, which means that to some extent in the Hamiltonian formulation, the Hamiltonian has to be self-adjoint. But it's not the only principle, because we know that there are other symmetries which have to be also enforced, as I said, otherwise you violate the conservation of these symmetries by boundary effects. One of the interesting symmetries is the U1 symmetry of quantum field theory for charged fields. This U1 symmetry implies charge conservations on the system, Gauss law and so on. But there are systems which are neutral and they do not have this U1 symmetry, so you cannot apply the symmetry to fix the boundary conditions. And then what to do for those systems? Any system which is in relativistic quantum field theory has Poincare invariance in the Minkowski background. So this symmetry, in particular time translation and space-time translations, imply new conservations law. Time translation implies energy conservation, which to some extent is connected with unitarity. And so this is one principle which applies to all field theories, not only the ones which have a U1 symmetry, so which involve charged fields. And this is the way we were having explored it in the last years with Fernando Esquerro. Let me just take a few examples to explain how this works. So let's consider the simplest model is a real scalar field in a half space. So you have a normal Lagrangian with self-interacting Lagrangian, and due to this time and space-time translations, you have currents, four currents which are conserved, which are associated to the energy momentum tensor. So in this case, the energy momentum tensor takes this form, and in any classical solution of the equation of motion satisfies this identity. So if we just concentrate in the zero component of the energy momentum tensor, we have this energy conservation law, which it means that the time derivative of energy density plus the divergence of the linear momentum density equal to zero. So in this particular case, the energy density is given by this expression, whereas the linear momentum density has the one in the bottom of the slide. First, I have to apologize because my voice is not working properly because I got a cough last 2 days ago, and so I'm still recovering. Okay. So the energy conservation law implies that the time variation of the energy contained in a bounded domain, omega, is equal to minus, there is a missing minus here in this formula, of the flux of the linear momentum across. So this is the identity. And so in this sense, we say that the energy is conserved because it might change, but we understand that this change is due to the flux of the linear momentum on the boundary. Applying this conservation law to a particular case where you have half a space, the upper half a space, taking as boundary the x3 equal to 0, gives this identity where the variation of the energy in a bounded domain is equal to this integral of phi dot phi prime. Phi dot is the time derivative of the scalar field evaluated at the boundary. And phi prime is the normal derivative of this field at the boundary. So the only way of matching this condition equal to 0 is that both one of the two derivatives vanish. If the time derivative vanishes, we have a static boundary condition, and this is connected with what is the deep brain physics in string theory. The other boundary condition, so there are only two boundary conditions which are homogeneous, so are uniform on this boundary, which is just the hyperplane x3 equal to 0. The other one is phi prime equal to 0. So it's the normal derivative of the scalar field equal to 0. This is the usual boundary condition which is used in open string theory. So there are only two choices. But if we go to complex scalar fields, the theory becomes richer, and we repeat the same scheme, and assuming translation invariance on this hyperplane, we found that there is the most general boundary condition is given by unitary matrix connecting the boundary values of the time derivative of the fields or the normal derivatives in this particular way. There is no other way out to preserve energy in the bounded domain. So this unitary matrix is belongs to U2 in this case, but because you can take the complex of this identity and you have to satisfy also another identity in that case, it means that there is an extra condition. The extra condition is that the unitary matrix is not unconstrained. This unitary matrix will satisfy this identity together with the complex conjugate. So, in general, the boundary condition is given by unitary matrix, which also belongs to the orthogonal group O11. And this is one-dimensional. So, subgroup, which has two components, the one associated to the unitary matrix with determinant +1, and the other component is given by the unitary matrix with determinant -1. In terms of boundary conditions, the matrix, the two independent families, one-dimensional families are this one, U plus and U minus, with the parameter A and B each one, which are angle. And the explicit boundary conditions associated to this generic choice of this unitary matrix is that the normal derivative of the field at the boundary has to be proportional to the time derivative of the same field at the boundary with a constant, which is the cotangent of this angle A over 2. The same happens for the G minus component. It involves combination of phi dot and phi prime, which are normal and time derivatives of the field at the boundary, and the real and imaginary parts of these combinations are satisfying some constraint equation. Particular case of these boundary conditions are, for instance, when this unitary matrix is identity, of course, it satisfies all the requirements. In this case, the boundary condition you obtain is the static one, so phi dot at boundary has to be 0. When this matrix is -1, it's a two-dimensional matrix, then the boundary condition is phi prime equal to 0, so this is the usual Neumann boundary condition. And there are many more which are particular. For instance, this chiral boundary condition, which corresponds to U proportional to sigma 3. And then in this case, the normal derivative and the time derivative are related by this minus I or plus I coefficient. And the same happens when you have a choice with a different Pauli matrices for this unitary matrix, which is plus or minus sigma 1. And in this case, you get what is known as twisted boundary conditions, which involve real and imaginary components of the normal derivative and the time derivative of the fields. And another interesting example is the one which corresponds to sigma 2. You see sigma 3, sigma 1, sigma 2. And sigma 2 is a very particular type of boundary conditions where the real and imaginary part of the normal derivative and the real and imaginary part of the time derivative of the fields are proportional. So this is an interesting example. And all of these boundary conditions give rise to different set of solutions. And in the quantum field theoretical case, you have different, for instance, Casimir energies. If you have two plates, which is the setup appropriate for the discussion of the Casimir phenomena, you can repeat the procedure, but then you have a richer choice. So the unitary matrix associated to the most general boundary condition is a matrix, four-dimensional unitary matrix. So it's a matrix 4 times 4, and connects combinations of time and space and normal derivatives in both sides of the 2 plates and the 2 different sign combinations. So you have 4 independent combinations, and so your matrix is 4-dimensional. Again, there is a constraint due to the fact that this matrix has to satisfy also the same equations for the complex conjugation of the identity. So finally, the matrix which give the most general boundary condition is a matrix which belongs to a 6-dimensional subgroup of the U4, which is the subgroup given by the intersection of the unitary matrix with the orthogonal group, O2, 2. And this can be generalized to higher dimensions and to more setups with different plates. And finally, the type of unitary matrix involved in these boundary conditions take this form in the case of determinant +1 and the second family, which generates the second component of the boundary conditions is obtained from the first one just by multiplying by this unitary matrix, which has determinant -1. So examples of that involve the same situations as before: Neumann at both sides, static boundary conditions at both sides, at both plates. But you have new boundary conditions, which are periodic boundary conditions connecting the 2 plates, and anti-periodic, and many more. But these are very well-known examples, which still preserve energy in the quantum field. So the interesting thing is that this approach for the scalar field is not novel, because you have charge conservation principles which give rise to similar boundary conditions, but it's very important in the case of gauge fields, because in the case of gauge fields, you don't have the possibility of using charge conservation as a basic principle, because the charge conservation for gauge fields gives a tautological identity. Is why is the second Nether theorem, which doesn't helps in establishing boundary condition. So, but if we apply energy conservation to these neutral fields, as we did in the case of real scalar, to case of gauge fields, in particular electromagnetic field, you have very good foundations to formulate the theory of boundary conditions. In this case, you have, for instance, the Maxwell theory. You have the energy momentum tensor, which is conserved in that case, which is well known in this form. And then again, you have the energy conservation of the energy density, which is E squared plus V squared, electric field squared plus magnetic field squared. And the momentum component is just the standard Pontryagin vector density. So the conservation of energy involves that energy is preserved in a bounded domain, in the sense that the change of energy is equal to the flux of linear momentum across the surface, as we did in the general case. So considering a particular configuration of half space, as we did in the scale field, you have that the more general boundary condition is given by a unitary matrix, which connects the tangential components of electric and magnetic fields, and an extra condition, because the electromagnetic fields are real, and then the unitary matrix has to satisfy this condition, which essentially tells you that this unitary matrix has to also belong to the O11 group. So again, we have one-dimensional group of boundary conditions with 2 components. The determinant +1 component is always of this form, and in practice involves a combination of a linear dependence of the components E2 and B2 of the electric and magnetic fields, and they are related to E1 and B1 of the same fields, up to a constant. And the other component is more symmetric in the sense that it involves linear dependence of the two components of the magnetic field with the two components of the electric field, tangentials to the surface, to the boundary surface. So here you have a bunch of examples, which are, for instance, the simplest one, which is the identity, implies the vanishing of the second component of the electric and magnetic fields. And the case where this unitary matrix is -1, you have the vanishing of the first components of this electric and magnetic field. But one different case is this U plus matrix, which is proportional to sigma 3. And in that case, the two components, the two tangential components of the electric field are proportional up to a sign. And the same happens with the magnetic components. They are identical up to a sign. So this is a very interesting boundary condition, which of course implies the vanishing of the Pointry eigenvector, because you have the vector product of two objects which are the simplest, and they give 0. The product gives 0. So another case in the second component, the one which has the determinant -1, is sigma 1, where two components, so magnetic field equal to 0 on the boundary, and equal to minus sigma 1 is the electric field vanishing on the plate. And the last one, there are many others interesting, but I have to cut the list to this point. The last one I consider here is the one where U matrix is proportional to sigma 2, up to a sign. So in this case, the electric field and the magnetic field are parallel or anti-parallel. So it's obvious that in this case, the Pointry eigenvector also vanishes. And this is one interesting boundary condition. And you can compute the Casimir energy with this boundary condition, and you get very different results from the previous one. So in the case of more complex vector fields, so you have, for instance, so far we have formulated the boundary conditions in terms of electric and magnetic fields, but you can go beyond and try to formulate the boundary conditions in terms of electromagnetic potential, because you are in the Maxwell theory and everything can be formulated should be formulated for the dynamics in terms of electromagnetic potential. In this case, the first kind of boundary conditions, which are the ones which have determinant +1, imply in terms of vector potentials in the Lorentz gauge. Here we have to fix a gauge, and Lorentz gauge is very convenient because it preserves covariance. In that case, you get this type of boundary conditions for the electromagnetic potential. So you have the derivative along the two dimension, which is tangential direction to the plate of the boundary, is an Hermitian matrix involving all the derivatives 1 and 3 space partial with respect to x1, partial with respect to x3, and partial with respect to time. But all of them in a self-adjoint matrix times the vector potential. So this is what you get in charged fields when you consider the current conservation, the U1 symmetry, but not for these fields, and it's quite similar, in spite of the fact that they are neutral. So for the other component, it's even more interesting because the kind of the generic boundary condition you get for this point geometry is just that the normal derivatives of all special components of the vector potential are derived from the vector components of this potential, with again a Hermitian matrix, which involves derivatives along the tangential directions, d1 and d2, and also some time derivative in the first two components. So from this viewpoint, the energy conservation principle leads to very simple and natural boundary conditions for vector potentials derived from first principles. In the case you have two plates, again, the same can be done. The only problem is that the mathematics is more involved. You have four components. Your matrix is, belongs to U4, but as we have been emphasizing along this talk, there is an extra condition because the vector potentials are also real functions. So the unitary matrix has to match this condition, which in fact implies that it should belong to O to 2. So in this case, we have a 6-dimensional group of boundary conditions, and the typical geometry is that you have two components, one which is connected to the identity, but it can be formulated with an exponential, as we do here. It's an exponential of an Hermitian matrix. So it's unitary, of course. And the other component, which has the term -1, is obtained from this component connected to the identity just by multiplying by parity of the matrix. And in this slide, you have the most general type of boundary conditions you can have for the two plates configuration engaged in electromagnetic theory with the geometry of two parallel plates. You can generalize this to Young-Mills theory, and it's very nice because everything preserves gauge invariance. So, but I don't have time to enter into the details. But you have the same picture. You have boundary conditions in terms of field strength components, which are, of course, have color. But the main point is that the unitary matrix should be trivial on color space, so proportional to identity. But once you impose that, the rest follows immediately. So for the coming back to the electromagnetic case, you have some particular examples which are quite similar to the ones for the scalar fields, but in the electromagnetic theory have a more surprising condition. So, for instance, this anti-symmetric, this zero identity zero matrix, which satisfies all the conditions, have all magnetic fields in both plates vanishing, all components, which are tangential. The same happens with this choice, with a minus sign here, for the electric field. So with this choice of boundary conditions, all electric fields vanish on the boundary, all tangential electric fields. And finally, there is a more peculiar type of boundary condition given by the unitary matrix, which is proportional to diagonal sigma 1. And in this case, the electric field components in one plate are related with electric field components in the other plate. So E1 and E2 are the two components, tangential components in one of the plates, and E3, E4 are the tangential components in the other plate. This is our convention. The same happens for the magnetic field. So this boundary condition implies that the fields are periodic or anti-periodic. And so you recover these natural boundary conditions by these principles. There are some conditions which are currently used in electromagnetism, which are not in this framework, but it can be obtained just by imposing extra requirements. So, for instance, if you you want to have a stable electronic situations on the boundary, then you have extra requirements, and with these extra requirements, you find the standard boundary conditions that appear in the literature. So I'm almost done, so let me just summarize the conclusions. First, as I emphasized at the beginning, the boundary values are essential to establish the Nether theorem, because usually in establishing Euler-Lagrange equations, you fix the boundary values at the extreme points of the fields. And to obtain the Nether theorem, you have to relax this condition. Okay, perhaps using this Schwinger approach that Beppe Marmo was telling us before, you can understand it better. The boundary conditions should be associated to conservation laws. They are not coming for free. So if you don't impose any principle, you don't have boundary conditions. You can have any arbitrary boundary condition. So you have to establish what is the principles to fix the boundary conditions, and the most reasonable one is to associate it to a conservation law. It might be a U1 symmetry, or it might be this time translation symmetry, which is the one we have been exploring with Fernando in the last year. The charge preserving boundary conditions is very natural. It has been used in the past, but it doesn't work for neutral engaged fields, which are very important in the standard model. So the way out of this constraint is just to replace these charge preserving boundary conditions by energy preserving boundary conditions. And this can implement it, I have shown, not for the case of gauge fields, but I mean, you can trust me, it works also for gauge fields. It works for any field, even fermionic fields too, with a spin not lower than 2. The reason why it doesn't work for spin 2, in the case of Magler's theory, which is gravity-Einstein theory, because in this case, you obtain a tautology, because the Einstein-Hilbert-Lagrangian, for instance, is invariant under D, and this invariance doesn't tell you that there is a conservation law, so you cannot proceed. But there is another way, which I don't have time to tell you, but which also you can get the boundary conditions for gravity. Following this principle, you have to find another symmetry, which gives you the rules to establish the right boundary conditions. And this is all. I would like to finish thanking to Val for all these years of discussions and insights and inspiration. Thank you.
Thank you, Professor Asure, for the nice talk. We have time for questions.
Hello, Manolo, can you hear me? This is Kumar.
Sure, yes.
Hi. Okay, I have a question regarding the first part of your talk. See, if I were to look at quantum mechanics, not say quantum field theory yet, then we know that there are examples like conformal quantum mechanics, for example, where the form of the potential can make a difference in the boundary conditions which are applicable from a unitarity point of view. So here in this discussion, I mean, I didn't understand completely, but it seems to me that the potential, at least in the scalar field part, did not play too much role in your analysis of boundary conditions. So
you are right. You are right. We discussed the case of local quantum field theories. So it means that you can you don't have singular self-interacting potentials. It's just polynomial ones or local and even more than local, is polynomial ones. Of course, in quantum mechanics, you have more freedom because, you know, there is no this strong requirement of renormalizability. And then you can play with very, very singular potentials like the 1 over r squared, which is the one you perhaps have in mind. So in that case, of course, everything changes, everything. So you cannot, if you, as you notice, everything here is driven by the kinetic. The potential part, the local part, doesn't play any role, as you already emphasized it. But in the case where you have these singular potentials, Hamiltonian operator, there is also a theory, but it's not the one we have. You mentioned is not based in the symmetry principle. It's just illusion, if you wish, which might be related to U1 symmetry in the Schrodinger picture.
Thanks for a nice talk, Manuel. I think you're restricted to the case where there are no degrees of freedom on the boundary, which was coming from your translation invariance in the absence of boundaries. How difficult is it to just consider additional degrees of freedom in the boundary? It's natural to consider some delta function potential close to the boundary in the scalar case. It leads to boundary conditions like the normal derivative being proportional with some constant to the field.
Yeah.
Is that interesting?
So this is a question that Bal asked me many times. But in the case you are interested, you have to split your theory into theories. One which is on the bulk, the other one which is in the boundary. And you fix the bulk with the boundary conditions, but then you add degrees of freedom on the boundary, and then you have interaction between both, right? And there are many examples, and also you have been working on some of those. You know very well what's going on. But this part, which we are studying, is just the one where there is no degrees of freedom on the boundary. In fact, there is one constant degree of freedom on the boundary, but it's not very rich, as you can imagine. You would like to have more freedom of gauge fields on the boundary. So this fixes the problem for bulk dynamics and fixing the boundary conditions. To go beyond that, you have to work.
The one I had especially in mind was the one which is natural for the functional Schrodinger equation, which is on the half line. You require
yes,
even you require to renormalize the boundary conditions on the.
Yeah. Another example where this is very useful is Chern-Simons theory. You know, where you have in the boundary some pure Chern-Simons. You have chiral and sigma model. You know, is another one. Yes. But I cannot say anything from this perspective about that.
Yeah, but
can you? Okay. If I take quantum mechanics, in fact, you have worked with Alberto and Beppe, and some Juan Manuel maybe. If you get an elliptic operator, which in quantum mechanics, plus let us say a smooth potential, and to find the Hamiltonian in a, say, region with the boundary, what one gets is all unitary operators from one infinite dimensional Hilbert space you can attach at the boundary to another one, okay, which you wrote in terms of phi dot, then phi prime minus phi dot, I think, at the boundary, and the plus one. Okay, there were two Hilbert spaces, and you consider any isometry between them, and that will give a boundary condition. Okay? And the Hamiltonian cannot change, the time evolution cannot change it because that will change the domain. And you can second quantize it. Now, this is for standard Laplacians. But what happens if you have operators with more derivatives, as you are considering, or in gauge series, this apparently does not work. There also you get a differential operator, okay, a second order differential operator, which presumably is elliptic. So what happens there?
It's hyperbolic. So you just touched the point. So my motivation for this work is exactly to answer.
But you had to go through the energy movement tensor.
The answer came in two steps.
So
one was down in lectures I gave in Bangalore some 5 years ago, something like that. And it was based on the imposing U1 symmetry as a rule to establishing boundary conditions. And once you do that, you obtain the same picture as the one you mentioned with Pepe and Alberto. It's just infinite dimensional unitary operators and so on. But we were frustrated by the fact that this formalism did not apply to fields or to gauge fields. And this work we have done now is the continuation. So the idea is that I focus on very simple finite dimensional unitary groups because I impose homogeneous behavior on the boundary. But if you have more general boundary, even if it is flat like this one, you do not impose translation symmetry on the boundary, then you have again the infinite dimensional unitary groups, exactly the same as in the case of quantum mechanics, exactly the same. But the boundary conditions are different because we are dealing with hyperbolic problem. You have a second order differential operator, and we are not imposing hermeticity of this operator. We are imposing conservation of charge or conservation of energy, which is different. But the rest works exactly the same. So we follow the same rules. I don't know if did I answer your question properly? Well,
maybe, I'm not sure, because what I do know is that the differential operators with time included in a, say, gauge theory, that operators, the connection field is not an operator on a Hilbert space. Because of the fact that there are time-like components, it is not an operator, it's an operator on a Krein space. But the, yeah, so it is not an operator, it's not a Hilbert space operator. So I don't know whether the standard analysis of Self-Join extensions apply to such operators which act on a Krein space, indefinite metric space. I don't know. I don't know. I don't know if a theory.
Yeah, this is what we claim. It works. So you don't have positive works.
Okay. Manolo, could I see the conclusion page that you have? Yeah, I couldn't, it's just a curious observation that you have difficulty for boundary conditions for gravity fields and also for the spin-one fields. It's very reminiscent of what happens with the Weinberg-Witten theorem. I was wondering, right. Do you know any connection, or is it just completely off the wall?
One day I thought about it, but I have not found any direct connection. But it's very interesting remark, because essentially what happens with Weinberg theorem, Weinberg-Witten too, is that the problem is the massless, the infrared behavior of these particles, massless particles with higher spin. And of course, the problem is associated to the conservation laws. For instance, the energy momentum conservation law in the case of gravity is again behind the theorem by Weinberg. And here is exactly the same. So, but I don't see any connection, because I think that even if I have massive gravity models here, I do still have the same problem. You understand? It's not a matter of being massless. the particles behind the quantization of the gravitation field, but it's just a matter of having deep invariance. So it's more, is deeper. So, but I could not find any direct connection between both things. That's very interesting remark. Thank you.
Okay, I have a small question. Is there any guideline for boundary conditions in dissipative systems? Dissipative systems.
Not in this picture, but I never thought about it. But I'm pretty sure that there should be, because the essential point is that you have to determine, for instance, talking about classical field, right? You have to determine the evolution in a unique way. So, for instance, if you have a second-order differential operator, you have an alternative problem, which is the Cauchy problem. It's exactly boundary conditions in another way, but it's a boundary conditions problem. In fact, in our picture here, some of the choices are connected with the Cauchy problem. So you have to determine, if you want to have a well-defined dynamical system, you have to determine unique solution, provide some initial data. This data can be initial in the Cauchy sense, or can be boundary values in this picture we follow here. So you have to determine. In the case of, you mentioned, you have dissipation, so you cannot use the energy conservation law, but you still have to fix some conditions to determine unique solution of your dynamical system. And in any case, you have to determine boundary conditions associated to the dynamics of the system. I know some examples where these have been done, but they are kind of toy models. But the principles we are following do not apply in that case, because we choose exactly the opposite direction. So just enforce the energy conservation, which is in the dissipative system schema, is impossible, right?
Can I speak? Manolo, ciao. This is Giorgio Mirzi.
Oh, Giorgio, ciao.
Ciao. I was wondering, I mean, boundary conditions are okay, but for half space. But if I think a whole space, then I have a question of reflections, which are an interest of which have an interest of their own. If you want to impose conditions of what happens under reflections, which is very tricky in the case of gauge fields. I mean, it's trivial non-trivial, but it can be done in the case of scalar fields, but in the case of gauge fields, gets very tricky. To say
you
nothing.
You mean a space reflection, not because here we are. So in our case, we have a special plates and infinite time, so they are static, so they are forever. These boundaries, they are static. So this is a fixed picture. You're referring to that picture, no? Space-time surface, no? Sorry, a space surface. So for the scalar case, this has been solved, so there is no problem with reflection. In fact, boundary conditions sometimes solve the problem at once. You don't have to, for instance, you have, sometimes you get some boundary conditions just by iterating some reflection procedure. But if you solve the Poisson equation, you get the solution at once, so you don't have to iterate. In the case of gauge fields, I have not looked at that, because gauge fields have a special transformation under, for instance, reflection, no? But I'm pretty sure it can be done, because this is adding a symmetry. Adding symmetries is good. It restricts the general setup of boundary conditions. So you have a room for restriction, but I have not looked at the problem. But what is your worry? Is that maybe...
Well, if you want to know what I'm worried about, is the fact that if you have spin-off fields, for example, and you start asking questions about tricky questions about chiral spin-off fields, you see, and then you have a reflection, and there is certainly a case in which, for example, the positivity does not work because, and you know that it doesn't, but I don't know how to prove it.
Yeah.
I worried about this for a long time, but I never got anywhere.
You
maybe,
mean space
maybe we could continue the discussions later because we are spilled over time. Yeah. If there are no more questions, let's thank the speaker again. The last speaker of this session is Idri. Professor Idri, can you hear us? Yes. I'm asking Professor Idri. Yeah. Professor Idri, please unmute and speak to us.
Yes, you hear me now?
Yeah, we can hear you.
Yes, I'm sorry to, so shall I just start the talk or?
No, we have time for you though.
Okay.
Yeah, please share your screen with us.
I'm trying to do that. I don't know, not really familiar with Zoom. It's my second time using Zoom. You see now the slides? Hello?
We still cannot see your slides. Please share the screen. Yeah, the previous speaker's screen is still there. Okay, Professor Asuri, you may please stop sharing your screen. So what? Professor Idri, please share your screen with us.
Yes, I'm trying to do that. I'm not sure how to do it.
Yep. Okay, that option is in the bottom of your screen. Yeah,
yes.
Green color.
Green color, yes.
Yeah. If you click on that, you will see the options. is not able to do it in the next 5 minutes, we can postpone. Shall we ask him to send the file? If PDF is there. Yeah, we are able to see it.
We see it now?
Yes. Could you please make it full screen? Yeah. So the next talk is by Professor Badi Sidri, and he will talk about non-commutative geometry, matrix quantum mechanics, and the correspondence between them.
Yes.
Professor Idri, please.
Thanks very much. Sorry for this delay. So do you hear me? Shall I start? Hello, can I start the talk?
Yeah, please.
Yes, so I would like to talk briefly about quantum mechanics and the correspondence between quantum mechanics and non-commutative geometry. So I take as an example quantitative space-time in 2 dimensions. We will quantize ADS2, which tries to write down a matrix model which will capture the essential features of non-commutative ADS2. And then we will describe the phase diagram and try to see if we have an information loss problem on ADS2. The second bit, I have time, I will try to discuss the quantum mechanical dual, so this theory. And then I will conclude with a brief discussion of the correspondence between non-commutative ADS2 and the quantum mechanics of the AFF, the so-called conformal quantum mechanics. So we know that in Euclidean dimensions, in 2 Euclidean dimensions, we have 2 positive curvature spaces, S2, and the pseudosphere, H2. The pseudosphere is our Euclidean ADS2. So we are mostly interested in Euclidean ADS2, but so the discussion will be more rigorous. And of course, Euclidean ADS2 or the pseudosphere is related to the anti-DC effect by standard Wick rotation. The quantization of the sphere is known to be given by the fuzzy sphere. The quantization of the pseudosphere is given by the non-commutative pseudosphere H2 theta. They have the same isometry groups as the commutative spaces. The fuzzy sphere is known to be unstable, so we know this. So the fuzzy sphere is unstable, and it evaporates in the phase transition to an Euclidean Young-Mills phase. This is a geometrical phase transition, which we also call emergent geometry. This is a known result. We will also show that non-commutative pseudosphere or Euclidean ADS2 is also unstable and can evaporate in a phase transition to a Lorentzian Young-Mills model. This is also an emergent geometry transition. However, the non-commutative pseudosphere can also sustain black hole configurations across including dilaton tip. We need to include dilaton tip, which we will do in a short moment. This configuration can suffer collapse in the form of the so-called information loss problem. What we do, this for us is precisely a gravitational phase transition or emergent gravity. The fact that we have the possibility of a dilaton field this will present itself in our description as an emergent gravity or emergent gravitational phase. Also, we will show that the emergent gravity transition is actually the inverse process of the gravitational information loss problem. So our understanding of the information loss problem is the fact that it is the inverse process of this emergent gravity. So we have an emergent geometry that is the emergence of the pseudosphere from a young Hills model, but we also have an emergent gravity that is the emergence of a black hole, of an ADS2 black hole configuration from pure ADS2. And this transition, the inverse of this transition is our information loss process. So all these geometrical and gravitational information loss processes are strictly speaking unitary processes. They are all occurring in path integral quantization, of Young-Mills matrix models of the IKKT type. So they are unitary processes. So we have, in summary, the following phase transitions or the following phases: a gravitational phase, in which we have a dilaton field. So the dilaton field acquires an expectation value, and the gauge field acquires also an expectation value. A geometrical phase in which the gauge field only condenses, the dilaton field is zero, and we have a Young-Mills phase in which none of the fields condense. All of them have zero expectation value. These are the three phases of that we have in this Young-Mills matrix model, which I will write shortly. And they are, as I said, unitary processes. These are ordinary phase transitions. We can also specify the degree. So they are unitary processes in path integral quantization. So clearly, or what I explained is that we have really no information loss problem in this non-commutative model. In the commutative limit of these Young-Mills matrix models, what we have, the mesh description becomes unavailable, and we are back to the usual descriptions of the black hole evaporation process, where seemingly information is lost. This is the main method of this talk, really. So we have really, in this description of, in our description of non-commutative black holes, non-commutative ADS2 black holes, we have an instability. We have really an emergent gravity phase condition, but we do not really have an information loss problem because it is simply a unitary process. Let me start by giving a brief discussion of the non-commutative sphere or non-commutative Euclidean ADS2. So this is the quantization of symplectic space, symplectic manifold. It has a symplectic structure which can be quantized in the usual way. And the answer is a non-commutative space given by certain irreducible representations of the group XO12, which is the group isometry group of H2. So the isometry equation 2 gives me ADS2 as embedded in 3 dimensions, in Minkowski space of 3-dimensional size. So this is our ADS2. And the quantization of this space simply reproduces the usual, irreducible representation of SO12. Clearly, this surface has an SO12 isometry group. So the relevant for Euclidean, the pseudosphere or Euclidean ADS2 is really given by this embedding condition, but also is given by these commutations correlations. The x hat are the coordinate operators on ADS2. The structure constants are precisely the structure constants of the group SO12. Kappa is here, this number is the deformation parameter. The irreducible representations we are talking about, these Ka are given by the irreducible representation of SO12 given by the discrete series. So these are standard representations which we recover for Euclidean ADS2. For Lorentzian ADS2, we will obtain the continuous series. But the difference is really at this stage, difference is really only in the type of representation which we cover. However, for us, non-congruous ADS2 is obtained via weak rotation of Euclidean ADS2. We can really understand the quantization of Euclidean state. Quantization of a Lorentzian state is really troublesome, and it's really only a formal really. So this is the structure. This is our non-congruous ADS2 given by equation 3, and the irreducible representations of the discrete series of SO1. Just word on the commutative limit. We can relate the deformation parameter kappa with the radius of the ADS2, and also the pseudo-spin quantum number K. So the group SO12 comes with the irreducible representation given by the discrete series of the group SO12 comes with a pseudo-spin quantum number, which is here denoted by K. So this is the relation which relates the main parameters of the model. So the radius, the deformation parameter, and the pseudo-spin quantum number. So the commutative limit really is given by kappa goes to 0 or K goes to infinity. This is exactly what happens also on the top here. So this is the commutative limit. Now we write the gauge theory. So the idea is simply to replace this coordinate operator, and simply replace this coordinate operators with some gauge covariant operator. So we introduce a UN gauge symmetry by substituting the coordinate operator by some matrix TA, which transform unitarily, which transform under UN gauge transformation in the usual way. So I write a field strength. This, if I replace the A by the coordinate operator, I get 0. It's exactly this statement. It's exactly this commutation relation. However, now I replace this configuration by pure gauge configuration, which are given by U, X, hat, E, U, that. Then I include non-trivial field configuration by adding some connection, kappa, A, R, and I write an action which is given by the usual Young action. I take here a complete square, which is I take F squared, where F is the field strength, and I write this matrix model. This is matrix model I would like to study. The parameters here are given by this alpha, which is the parameter chance and return. This is the relative deformation parameter as in equation 8. But we have also some master data. I will not discuss so I can discuss actually the phase diagram of this model in alpha plane, but really what interests us is the data equals 0 value. That is sufficient really to obtain the flavor of what's going on. So I simply go directly to so I simply set this mass parameter beta to 0, and I study the model. What I find that there is there is only a single parameter, which is this alpha. Here, chance time first. This will play the role of the inverse temperature. The inverse temperature, the metric temperature, not the Hawking temperature. So T is equal to 1 over alpha theta 4 is the temperature of this model. As we increase this temperature, the non-commutative pseudosphere, the Euclidean ADS2, evaporates at empirical value alpha theta star to a Young-Mills metric space. The Young-Mills metric space has no background geometry structure at this stage. I can say more on this if I have time, but for the time being, there is no background geometry structure here in the Young-Mills metric space. So we have a phase transition at some critical point alpha tilde star between a pseudo-clear phase and a Young-Mills phase. This is the essential behavior. Really. The order parameter here, I took it to be precisely chance dimension, nothing more, just a chance dimension. If I now would like to study this model in the alpha beta plane, I will find a picture like this. This is actually the phase diagram on the fuzzy sphere, but this is precisely the phase diagram. This is what I conjecture here is that this is precisely the phase diagram on Bolivian ADS2 on the pseudosphere. So there will be a pseudosphere phase, and there will be a mesh phase, and there is a line, critical line, consistent line between them, which will saturate at some value, which is precisely also true overnight in both models. So this is the picture in general, and the order parameter can be taken to be the chance time. It is non-zero in the pseudosphere phase, and it is zero in the Young phase. It is actually the term responsible for the emergent zone, for the condensation of the zone. Now I would like to add black hole. I would like to add ADS to black hole. So I need to add a Dilaton field. So there is no way around it. So we cannot have stable configuration in 2 dimensions, stable black hole configuration in 2 dimensions without a Dilaton field. So I will take back the signature. As I said, the discrete series relative this is replaced by the continuous series. This is now we are already now talking about non-commutative Lorentz in ABS2. I write the goal and I simply say what is our goal. I would like to write down non-commutative ABS2. Non-commutative Dilaton. I would like to write down 4-dimensional using a 4-dimensional Young matrix model. Remember, the Young matrix model is 3 dimensions. Now I will have a 4-dimensional matrix. I will have an extra. The phase structure will also so the phase structure is previous case is the phase and the phase will also go to the third phase, which is the galactic phase. And now the evaporation of the ADS theta black hole will present itself as a phase transition from the gravitational phase to the geometric phase. And there will be no informational problem in this document. The whole thing is a unitary box. All this is really
Professor Idri, may I interrupt you? Yeah, we are not able to hear you clearly. Maybe if you could switch off your video, then the voice will at least be clear. It is on the lower left corner, the video, lower left corner. Lower left corner in the Zoom screen. Yeah.
Yes?
Yes.
So did you hear me about the goals now? I would like to write.
Oh, it's a bit loud.
I would like to write non-commutative black hole solutions. This will include the Dilaton field. I would like to write a 4-dimensional Young-Mills matrix model. And I would like to study the phase diagram of this 4-dimensional Young-Mills model, of this 4-dimensional Young-Mills matrix model. And it will include 3 phases: a gravitational phase, a Young-Mills phase, and a geometrical phase. The evaporation of the ADS2 black hole will present as itself as a phase transition from the gravitational phase to the geometric phase. And there will be no information loss problem because the whole process is unitary. Do you hear me now? Hello? Do you hear me?
Yes, we can hear you better.
Thank you. So I would like to do that, if you don't mind. I just remind you about the black hole. So I would like to consider here the black hole, ADS2 black hole. So I write in equation 10 the usual pure ADS2 Poincare coordinates. Then I write the same space in Schwarzschild coordinates. They're equivalent. There is no black hole solution as such, but we notice that this metric equation 12, which is the ADS2 black hole in Schwarzschild coordinate, actually describes an ADS2 black hole solution if we include a Dilaton field. If you join this metric equation 12, if I join this equation 12, which gives me the metric of ADS2 space-time in Schwarzschild coordinate, I join it with the Dilaton field given precisely by this configuration, I get an ADS2 black hole. This is a solution of the celebrated Jacquiev Teitelbaum action. Everybody knows that. So this is our configuration. This is our ADS2 black hole configuration. Now I write it again here in this slide. So this is equation 15 is the pure ADS2. Equation 16 is the ADS2 black hole. The horizon is A by lambda, where A is this parameter. Lambda is the inverse radius. Lambda is 1 over R, where R is the radius of ADS2. And the mass and temperature of this configuration are listed in equation 17. They can be computed in the standard fashion. Now I would like to write the non-commutative configuration, the analog of this configuration in non-commutative geometry. So what I do, I simply rewrite the Dilaton field in terms of the embedding coordinate. I find that it is precisely proportional to x1. X1, remember, the coordinates of ADS2, the embedding coordinates of ADS2 are x0, x1, and x2. So phi is proportional to x1, 2p. T here is the Hawking temperature. It is not the matrix temperature. Now I quantize this by simply replacing everything by operator in the appropriate Hilbert spaces. That's the standard thing. So we simply replace x1 by the coordinate operator, x hat 1, and I get the non-commutative Dilaton field. This Dilaton field satisfies these commutation relations. You can simply use the commutation relations of non-commutative ADS2 to find these equations that needs to be satisfied by the Dilaton field or the Dilaton field operator. From these equations, I can even describe the Dilaton field using the Thalawin equation. This is a constraint on the Dilaton field that needs to be satisfied. Script K is the non-commutative derivation is given by the exterior derivative, the commutator with the SO12 generators. As it turns out, this is precisely the constraint satisfied by the commutative Dilaton field. The Dilaton field in the Jacquiev Teitelbaum model can be rewritten in terms of a nonlinear sigma model. This is a known result. I can rewrite the whole theory as a nonlinear sigma model. This is equation 24, where the ADM mass M is given by this constraint. So it's given by this constraint. Now, the commutative limit of our constraint is precisely this constraint. That is the statement. So we have really capturing the description of a non-commutative ADS2 black hole. It has the correct commutative limit. It has the correct commutative limit as a nonlinear sigma model, which is equivalent to the usual Jacquiev Teitelbaum model. Now, once we have reached this point, we are more confident that our description of the Dilaton field is indeed given by these commutation relations. Now, I would like to rewrite these commutation relations in a way that allows me to write a Yang-Mills matrix model for which the classical solutions are given by this Dilaton field plus the non-commutative ADS2. So I rewrite these commutation relations as a field strength, as in equation 26. So I simply rewrote it. So the extra structure constants are given explicitly in blue. Recall that the field strength which corresponded to the coordinate operators on ADS2 is given in equation 27. I put it 26 and 27, I get as general, I get a field strength in 4 dimensions. 27 is a field strength in 3 dimensions really. So I get a field strength in 4 dimensions, where the dilaton field is the coordinate operator number 3. So x hat 3 is identified with the dilaton field phi hat. So this is the field strength. Directly I can write now, I can generalize to gauge theory in the usual way, and I write a gauge action, and the gauge action will have these terms in it. The most important, this is the 4-dimensional Young-Mills matrix action. This is our gauge action. It describes quantum gravitational fluctuations about the non-commutative ADS2 black hole. The classical solution of this matrix model is given by the non-commutative ADS2 black hole. That's the statement. This matrix model includes two Chern-Simon terms. One responsible for the emergence of the geometry of ADS2. The other one, this one, is actually responsible for the condensation of the dilaton field. So there are 2 competing Chern-Simon terms, which causes the system to suffer 2 different phase transitions, a gravitational one and a geometric one. Let's simplify this model by simply putting the beta term to 0. I get this term here, and also simplify the Chern-Simon. This is the first one. This is the one responsible for the emergence of the ADS2 geometry. The second one is this one. This is the one responsible for the condensation of the dilaton field. D3 is the dilaton field, remember, recall our notation. Now we have, as before, 2 phases. So I can simply describe the phase structure. I can go through that. So the first Chern-Simon, this one, is responsible for the condensation of the non-commutative ADS2. This is emergent geometry. The second Chern-Simon, as I said, is responsible for the stability of the non-commutative ADS2 black hole, which means the condensation of the dilaton field. So this is an emergent gravity, and the inverse process is precisely the black hole evaporation process. So we have 2 critical points, alpha 1 and alpha 2, correspond to the vanishing of the 2 Chern-Simons expectation values. So I take as order parameters these Chern-Simons operators. So you have 3 phases. If I take alpha greater than the second critical value, alpha 2 critical, so we'll have the so-called black hole phase or gravitational phase. In this phase, the dilaton field is proportional to D1, and D are given by the coordinate operators x hat r. This is a gravitational phase in which the non-commutative ADS2 black hole is stable. If I take alpha between the second and the first critical point, the second Chern-Simon terms effectively vanishes, whereas the first one does not. So we have the dilaton field should condense around 0, whereas the dA, the matrix dA still fluctuates about the non-commutative ADS2 space-time. So we have here pure ADS2 phase. This is geometric phase. If we keep increasing the temperature, the matrix temperature here, by the way, there are 2 temperatures here, the matrix temperature, which is inversely proportional to this alpha, and the Hawking temperature. So if we keep increasing the temperature, which means increasing alpha, decreasing, sorry, this is a mistake, decreasing alpha below alpha 1, the ADS2 background itself will evaporate and to something called the Young-Mills matrix phase. All matrices fluctuate around 0. In summary, the Hawking process presents itself in this Young-Mills matrix model as a phase transition from the gravitational phase to the geometric phase. This is the inverse process of the emergent gravity geometry, of the emergent gravity transition. At this stage, so this is what I wanted to say about the non-commutative black hole. If I still have time, I would like to say something about the theory at the boundary of non-commutative ADS2.
Professor Idri, only 5 minutes.
Can I still continue? Do I still have time?
Yeah, 5 minutes more.
5 minutes. Okay, so I will just be quick then. I would like now to go to the boundary. So the boundary. I would like to go down to the boundary. So the boundary, the boundary of non-commutative. So the main statement is that the non-commutative the main statement is that the non-commutative ADS2 is asymptotically ADS2. That's the main statement, which means it has the same boundary as the commutative ADS2. They have the same boundary, and more than that, we can, and therefore there can be so it is one-dimensional or the ordinary boundary. So there is a conformal boundary located at z equals 0 in the usual Poincare coordinates. This is the usual boundary, which we know. This is also the boundary of non-commutative ADS2 theta. So this is the this is the region in which the dual conformal quantum mechanics resides. That's the principle. So I write this conformal quantum mechanics. So they take the boundary theory to be the usual DAFF quantum mechanics. So I can write the generators responsible for, so the generators of this DAFF quantum mechanics. These are given in equation 35. These are the usual translations and scale transformations and special conformal transformations. And I can also realize them explicitly in terms of either two remarks here are in order. First of all, this DAFF quantum mechanics does not include an SO12 invariant vacuum state. I don't have a state satisfied by this equation. And second of all, this quantum mechanics does not include primary operators in the usual sense. All I have are operators satisfying equation 42. Yet that is sufficient to reproduce all bulk operators. So the boundary operators, the boundary correlator operators computed using this quantum mechanics are precisely those computed in the bulk. So what we have, the only thing I have as vacuum, I don't have a vacuum annihilated by everything, by all operators. I do have only the lowest weight state. That's all I have. Also, I don't have primary operators in the usual sense. All I have are these coherent state kind of operators constructed here, and they satisfy this condition. So, yet this data is sufficient. This data is sufficient to construct a state boundary correspondence. So, and this is given by the red line in this line here. So this DAFF quantum mechanics is really not exactly conformal. It is what I call quasi-conformal. In the same, this is in the same way that non-commutative ADS2 is not exactly conformal. It is quasi-conformal. It is only asymptotically ADS. So this is the idea of this correspondence between quantum mechanics from one side and ADS2 from the other side. So the quantum mechanics is really quasi-conformal. So it's only quasi-conformal. And the ADS2 in the bulk must also be quasi-ADS, quasi-conformal, which is given by ADS2 theta. Furthermore, the algebra of the quasi-primary operators on the boundary is exactly sub-algebra of ADS2. This is very important. So the algebra of the quasi-primary operator, which we have constructed, is a sub-algebra of ADS2. And the Laplacian operator on ADS2 has the same spectrum as the Laplacian operator on ADS2. So the non-commutative ADS2 and the commutative ADS2 share the same spectra. So all these things allows me to say that really what we should take as a bulk theory for this DAFF quantum mechanics is non-commutative ADS2 theta, not commutative ADS2 as it is usually done. This is my other main message. So this is summarized here in this picture. So the bulk is really given by the algebra of non-commutative ADS2 theta. The bulk is non-commutative ADS2 theta. The boundary is asymptotically ADS, so it is the same boundary. So there is a quantum mechanics living there. That quantum mechanic, if we take it to be the DAFF quantum mechanics, is really not exactly conformal. It is quasi-conformal. So it seems to me it is much more natural to say that this quantum mechanics, this DAFF quantum mechanics, is dual, or it is the dual theory of the non-commutative ADS2 theta. And I stop here and thank you very much for your understanding. Do you hear me?
Thank you, Professor Idri. We have question for one or at most two questions.
Please go ahead.
Thanks, Matt. It's very nice to see you. This is Dinjo. I am wondering, is there any problem with the SU21 and the action that you're using being bounded from below?
That action, of course, is Lorentzian as it stands, even for the pseudosphere. So it needs a regularization.
Okay, all right.
Yes.
Sure.
Needs a regularization.
Okay.
As it stands, it is really, although we are talking about the pseudosphere, locally the pseudosphere is Euclidean, but the matrix model as it stands is a Lorentzian. So it needs regularization.
I think you'll probably be okay in the strict Largian limit, because
yeah, it is okay in that strict Largian and limit in the pseudosphere phase.
Yes, in the neighborhood of the pseudosphere phase. Yes. Okay. Thanks.
Yes. No problem. Right. In the other phase, you cannot simply. It requires some weak rotation and things like that, and regularization. The whole thing requires actually a regularization because this is an infinite dimensional matrix model. Yes.
If there are no more questions, let's thank the speaker again. Yeah, before we conclude, let's thank all the speakers of this session.
Thank you very much.
So there is an announcement for all the guests staying in Ginger and Pallavaram guest house. Your dinner will be in IMSC canteen across the road from this campus, and it will be served at 7:30. Please note that your vehicle to Ginger or Pallavaram will leave at 8:30. Yeah, tomorrow morning the vehicle will